Ancient ruins are often treated as the end of a story. In reality, they're usually the beginning of one. The moment a buried structure is uncovered, a new investigation begins. Who built it? How long was it used? What happened to the people who lived there? And perhaps most importantly, what has not been found yet? Many of history's greatest mysteries emerged only after archaeologists started digging. Hidden chambers appeared inside famous monuments. Entire cities were discovered where no one expected them. Long-accepted theories were overturned by a single excavation. The ancient world has a habit of revealing itself one piece at a time, never all at once. And that is why, even after centuries of research, some of its most important secrets may still be waiting beneath the next layer of earth. Perched above the Alazani Valley in eastern Georgia, Gremi was once the thriving capital of the Kingdom of Kakheti and a key crossroads linking Persia, Anatolia, the Black Sea, and the trade routes of the Silk Road. Although only fragments of the city remain today, its ruins reveal a remarkable story of innovation and ambition. Beneath the surviving towers, churches, and defensive walls lies evidence of sophisticated engineering that historians are still working to fully understand. Among all its mysteries, one stands above the rest: a ceramic water supply system that may have been one of the most advanced hydraulic networks in the region during the 16th century. The ruins of Gremi stand in Georgia's Kakheti region, approximately 175 kilometers east of Tbilisi. The city served as the capital of the Kingdom of Kakheti during the 16th century under King Levan. Although travelers had described the ruins for centuries, systematic archaeological investigations began during the 20th century and intensified after the 1930s. Excavations uncovered the remains of palaces, churches, baths, workshops, fortifications, roads, water systems, and residential districts. Archaeologists soon realized that the surviving fortress represented only a small part of a much larger urban center that once covered roughly 40 to 50 hectares. The first mystery concerns the ceramic water supply system. Water management has always been one of the defining characteristics of advanced civilizations. The Romans built aqueducts stretching for tens of kilometers. The Persians developed underground qanat systems capable of transporting groundwater across deserts. Yet Gremi presents a different puzzle. Archaeologists discovered networks of ceramic pipes buried beneath the city, connecting water sources with baths, fountains, administrative buildings, and residential areas. At first glance, ceramic pipes may not seem extraordinary. However, the engineering challenges become apparent when the terrain is examined. Gremi was built on elevated ground overlooking the Alazani Valley. Maintaining a consistent water flow across uneven slopes required careful calculations of gradient and pressure. Even a slight miscalculation could cause stagnation, pipe failure, or insufficient supply. The ceramic sections were manufactured with standardized dimensions and joined together with surprising precision. Modern surveys suggest that some pipe segments maintained gradients measured in only a few centimeters over significant distances. Such precision is comparable in principle to techniques employed by Roman hydraulic engineers centuries earlier. The greatest mystery is how the engineers surveyed the landscape. No written technical manuals survive. There is no evidence that the builders possessed advanced measuring instruments comparable to modern levels or transit equipment. Yet the water network functioned efficiently enough to support a growing capital city. Researchers continue debating whether the system evolved from local Caucasian traditions or whether Persian influence played a significant role. During the 16th century, the Caucasus stood at the crossroads of competing empires. Trade routes connected Gremi to Persian cities renowned for hydraulic engineering. It is possible that foreign craftsmen introduced specialized knowledge. Another possibility is even more fascinating. local engineers independently developed solutions adapted to the mountainous terrain of eastern Georgia. Comparisons with contemporary settlements highlight the achievement. Many fortified cities of the region relied primarily on wells and natural springs. Gremy appears to have integrated a planned distribution network, transforming water into an organized urban resource. This suggests a level of technical administration far beyond what many historians once assumed for the kingdom. The second mystery involves the fortress's hidden tunnel system. Historical accounts and archaeological evidence indicate the existence of a secret passage connecting the fortress to the nearby Unsolved River. Such passages were not uncommon in medieval fortifications, but constructing one beneath steep terrain presented enormous challenges. Excavations reveal that sections of the tunnel were cut through difficult geological formations while maintaining structural stability. Engineers had to prevent collapses, manage drainage, and conceal the entrance from potential attackers. Even today, not all portions of the passage have been fully investigated. The existence of the tunnel raises important questions. How extensive was the underground network? Was it intended solely for water access during sieges, or did it also function as an escape route and supply corridor? Some researchers believe additional unexplored sections may still remain buried beneath centuries of sediment. The third mystery concerns urban planning. Satellite surveys and archaeological excavations reveal that Gremy was not merely a fortress. It was a carefully organized city. Residential quarters, markets, workshops, religious buildings, and administrative centers were arranged according to a broader plan. Creating such a city required more than construction skills. It required surveying expertise, resource management, and logistical coordination. Tens of thousands of tons of stone, timber, bricks, and ceramic materials had to be transported and assembled. This challenge becomes even more impressive when compared with other regional capitals. Unlike cities built on broad plains, Gremy occupied a strategically elevated position. Engineers had to adapt streets, drainage systems, and foundations to uneven terrain while maintaining defensive effectiveness. Archaeological evidence indicates that workshops produced ceramics, metal goods, and construction materials locally. This suggests a highly organized economy capable of supporting large-scale building programs. Yet records explaining how labor was organized remain scarce. The fourth mystery centers on architectural technology. The surviving Archangel's Church demonstrates a blend of Georgian and Persian influences rarely seen elsewhere. Stone masonry, decorative brickwork, and glazed elements appear together in a unique architectural synthesis. The builders achieved remarkable structural stability despite the region's seismic activity. Earthquakes have affected the Caucasus throughout history, yet major portions of the complex survived for centuries. Researchers continue studying construction techniques used in the walls and foundations to understand how they resisted environmental stresses. Particularly intriguing is the combination of local stone and imported stylistic features. This mixture suggests extensive cultural exchange. However, historians still debate whether foreign specialists worked directly on the site or whether local craftsmen adapted imported ideas using indigenous methods. The fifth mystery involves defense engineering. The fortress occupies one of the most strategically advantageous locations in eastern Georgia. From its elevated position, defenders could observe movement across large sections of the Alazani Valley. Visibility extended across major transportation corridors connected to regional trade routes. The walls and towers were designed not only to resist attack, but also to maximize surveillance. Defensive architecture exploited natural terrain, reducing the need for massive artificial barriers. Similar principles appear in famous fortresses such as Krak des Chevaliers in Syria and the hilltop castles of Anatolia. Yet one question remains unresolved. How many soldiers were required to defend a city of this scale? Estimates vary significantly because surviving military records are incomplete. The relationship between the fortress itself and the broader urban population remains poorly understood. The sixth mystery is the city's sudden destruction. In 1615, Shah Abbas III of Persia launched a devastating campaign against Kakheti. Historical sources describe widespread destruction throughout the region. Gremy, despite its formidable defences and strategic importance, never fully recovered. The speed of the collapse surprises historians. A city possessing advanced infrastructure, strong fortifications, and regional economic importance should theoretically have been capable of prolonged resistance. Some scholars argue that gunpowder warfare fundamentally altered the balance. Defensive systems, optimized for earlier forms of siege warfare, became increasingly vulnerable to artillery. Others point to demographic disruption, economic devastation, and political instability. The precise sequence of events remains uncertain because surviving accounts are incomplete and often contradictory. What do you think was Gremy's greatest mystery? The ceramic water system, the hidden tunnel, or the lost engineering knowledge behind the entire city? Share your thoughts in the comments below. Armenia. More than 1,300 years ago, builders standing on a volcanic plain erected one of the largest domed churches of the early medieval world. Today, the dome is gone, the architects are forgotten, and their engineering methods were never recorded. Yet portions of their creation still stand, challenging modern assumptions about what 7th century builders were capable of achieving. The greatest mystery of Aruch is not simply how it was built, but how so much knowledge disappeared. The ruins lie in western Armenia, in Aragatsutn province, approximately 35 kilometers northwest of Yerevan. At the center stands the Cathedral of Aruch, constructed around AD 661-682 during the rule of Prince Grigor Mamikonian. Archaeologists first began serious investigations during the 19th century, while major excavations and restoration studies accelerated throughout the 20th century. What researchers uncovered revealed one of the most ambitious architectural projects in early Christian Armenia. The cathedral once measured roughly 34 by 17 meters and was crowned by a massive central dome. At the time of its construction, few churches anywhere in the world approached its scale. Compared with many contemporary churches in Western Europe, Aruch represented an engineering achievement of extraordinary ambition. The first mystery begins with the missing dome. No visitor today can see the original structure because it collapsed centuries ago. Archaeologists have reconstructed its appearance from surviving walls, foundations, architectural fragments, and comparisons with similar Armenian monuments. These studies suggest that the dome rose high above the central crossing, supported by an intricate system of arches and piers. The problem is that no construction manual survives. Modern engineers can model the loads using computer simulations, but the 7th century builders possessed neither modern mathematics nor structural software. Yet they successfully erected a dome spanning a vast interior space using locally quarried volcanic stone. This achievement becomes even more impressive when compared to contemporary European architecture. Many churches of the period remained relatively simple basilicas with wooden roofs. Aruch attempted something far more complex. A monumental stone structure capable of supporting enormous vertical and lateral forces. How did the builders calculate weight distribution? How did they determine the dimensions of supporting piers? How did they know which proportions would prevent catastrophic collapse during construction? The answers remain uncertain. The second mystery concerns earthquake resistance. Armenia occupies one of the most seismically active regions of Western Asia. Throughout history, earthquakes have repeatedly damaged cities, monasteries, and fortifications. Modern seismic studies show that powerful earthquakes have struck the region for thousands of years. Yet significant portions of Aruch survived more than 13 centuries. Researchers have identified several construction features that may have contributed to this durability. The builders used volcanic tuff, a relatively lightweight stone compared with the dense granite. Massive walls distributed structural loads across broad surfaces, while carefully arranged masonry courses appear designed to improve stability. Some architectural historians argue that Armenian builders developed practical earthquake-resistant techniques through generations of observation and experience. Others suggest that many surviving features may simply reflect architectural traditions rather than deliberate seismic engineering. The debate continues because direct evidence is limited. What remains remarkable is that a structure erected more than 1,300 years ago still stands in a region where earthquakes have repeatedly reshaped the landscape. The third mystery involves logistics. Building Aruch required enormous quantities of stone. Thousands of blocks had to be quarried, shaped, transported, and assembled with remarkable precision. The surrounding region contains volcanic formations suitable for construction, but moving multi-ton blocks across uneven terrain without modern machinery represented a major challenge. Similar questions surround famous sites such as Baalbek in Lebanon, where stone blocks weighing hundreds of tons were transported, and Sacsayhuaman in Peru, where massive stones were fitted together with astonishing precision. Aruch belongs to the same category of engineering puzzles. Researchers estimate that constructing a monument of this scale would have required a highly organized workforce, specialized craftsmen, transportation systems, food supplies, and administrative coordination. The cathedral was not merely a religious project. It was evidence of a society capable of mobilizing significant resources and technical expertise. The fourth mystery centers on surveying and geometry. Accurate planning was essential for constructing a symmetrical domed church. Every foundation, wall, arch, and pier had to align precisely with the overall design. Modern architectural analysis reveals proportional relationships throughout the building. The geometry appears intentional rather than accidental. Yet no measuring instruments associated with the construction have been discovered. No blueprints survive, and no written explanations describe the methods employed. Ancient builders across the Mediterranean often relied on ropes, plumb lines, measuring rods, and geometric rules transmitted through apprenticeship. The engineers of Aruch almost certainly possess similar knowledge. What remains unknown is the sophistication of their techniques. Did they inherit surveying methods from Roman and Byzantine traditions? Did local Armenian craftsmen develop their own systems? Or was the cathedral the product of centuries of accumulated experience, now largely lost to history? The fifth mystery, the most fascinating of all, concerns the giant wall paintings that once covered the cathedral. Most visitors focus on the architecture, but many overlook the fact that Aruch preserves some of the earliest surviving monumental frescoes in Armenia. Fragments discovered inside the cathedral reveal that the interior was once covered with enormous painted compositions. Among the most famous is a depiction believed to represent Christ accompanied by apostles and saints. Although only portions survive, the scale alone is extraordinary. These were not simple decorative images. They were monumental visual programs covering vast wall surfaces high above the floor, requiring sophisticated planning, skilled artists, durable pigments, and complex scaffolding systems. The first mystery involves the pigments themselves. After more than 13 centuries, traces of color remain visible. Scientific analysis suggests the artists used mineral-based pigments capable of surviving extreme environmental conditions. Red pigments were likely derived from iron oxides, black pigments may have originated from carbon-based materials, and other colors probably required carefully processed minerals obtained through trade or specialized local production. The exact recipes remain uncertain. Unlike modern paint manufacturers, Medieval craftsmen left no detailed chemical records. Many techniques were transmitted orally from master to apprentice, and when artistic traditions disappeared, much of the knowledge vanished with them. The second mystery concerns durability. Paint normally deteriorates rapidly when exposed to moisture, temperature fluctuations, and structural damage. Yet fragments at Aruch have survived more than 1,300 years. Why? Scientists believe several factors contributed. The mineral composition of the pigments may have enhanced stability. The preparation of plaster layers may have created unusually durable surfaces, and environmental conditions inside portions of the cathedral may also have slowed deterioration. However, researchers still cannot fully explain why certain sections survived while others disappeared completely. The third mystery concerns production. Creating frescoes on such a scale required extensive planning. Artists had to prepare walls, manufacture pigments, design compositions, erect scaffolding, and execute paintings before plaster dried. Large Byzantine fresco projects often involved teams of specialists working simultaneously. Did Aruch employ similar artistic workshops? Were the painters local Armenian masters? Or were they trained in artistic centres connected to Constantinople? The evidence remains inconclusive. Some scholars detect Byzantine influences in style and composition, while others emphasize distinctly Armenian characteristics. The result is a puzzle linking art, religion, politics, and technology. Which mystery of Aruch fascinates you the most? Let us know your thoughts in the comments below. Casa Karana is a stone mystery standing in the eastern desert of Jordan. Built more than 1,300 years ago, it looks like a fortress, functions like a palace, and behaves like neither. Behind its thick walls lies one of the most puzzling engineering achievements of the early Islamic world, a building whose true purpose remains unknown and whose environmental design still surprises modern researchers. The structure stands approximately 60 kilometers east of Amman, along an ancient route connecting Syria, Arabia, and Mesopotamia. Constructed during the Umayyad period, around the early 8th century AD, Casa Karana belongs to a group of monuments commonly called the Desert Castles. Yet, unlike many of its counterparts, almost every aspect of this building raises questions. The site became known to Western scholars during surveys of Transjordan in the late 19th and early 20th centuries. Systematic archaeological investigations later revealed inscriptions dating to around AD 710, making it one of the earliest surviving examples of Umayyad architecture. What researchers expected to be a simple desert fortress quickly became one of the most confusing architectural puzzles in the region. The first mystery begins with the building's appearance. Viewed from a distance, Casa Karana resembles a military stronghold. Its square plan measures roughly 35 meters on each side. Thick walls surround the structure. Massive corner towers dominate the skyline. Small openings punctuate the exterior. To travelers crossing the desert, it appears defensive and intimidating. However, closer examination reveals serious contradictions. Many windows are too large for effective defense. The towers offer limited military advantages. No substantial water supply exists to withstand a prolonged siege. Archaeologists have found little evidence of permanent garrisons or military activity. Compared with genuine frontier fortresses of the Byzantine or Roman worlds, Casa Karana would have been remarkably vulnerable. This contradiction has puzzled historians for decades. If it was designed as a fortress, why does it fail to meet many requirements of military architecture? If it was not a fortress, why was it deliberately constructed to resemble one? Some researchers believe the imposing exterior served a symbolic rather than military purpose. The building may have projected power and authority to tribal leaders traveling through the region. In this interpretation, the walls functioned as political theatre rather than battlefield defences. Yet the greatest mystery lies not in the walls, but in the air flowing through them. The deserts of Jordan experience extreme environmental conditions. Summer temperatures frequently exceed 40 degrees Celsius during the day, while nights can become dramatically cooler. Managing heat inside a stone building under such conditions presents a major engineering challenge. Modern architects solve this problem using computer simulations, thermal modeling, and mechanical ventilation systems. The builders of Qasr Karna had none of these tools. Nevertheless, they created an environmental control system that continues to impress specialists today. The building contains a carefully arranged network of windows, vents, corridors, and interior spaces designed to regulate airflow. Openings were positioned to capture prevailing winds while limiting direct solar heating. The central courtyard functions as a thermal moderator, encouraging natural air circulation throughout the structure. Thick stone walls act as thermal mass. During the day, the masonry absorbs heat slowly, preventing rapid temperature increases inside the rooms. At night, the stored heat is gradually released as exterior temperatures fall. This process reduces temperature fluctuations and improves comfort without mechanical systems. Modern passive cooling research demonstrates that thick masonry walls can significantly reduce interior heat gain in arid climates. Similar principles appear in traditional desert architecture from North Africa, Persia, and the Arabian Peninsula. Yet, Qasr Karna represents one of the earliest and most sophisticated surviving examples from the Islamic world. Researchers studying traditional thermal architecture often compare such systems to modern passive building designs. Today, architects spend millions of dollars developing energy-efficient structures that rely on airflow, thermal mass, and natural cooling. The Umayyad builders achieved many of the same objectives over a millennium ago using stone, geometry, and experience. What remains unexplained is how these builders acquired such detailed environmental knowledge. No engineering manuals survive describing the calculations. No architectural blueprints explain the airflow strategy. No written records reveal how builders determined the optimal size and placement of vents. Did they inherit knowledge from Roman and Byzantine engineers? Did they adapt techniques from Persian desert architecture? Or was the design the result of generations of observation and experimentation across the arid landscapes of the Middle East? The answers remain unknown. Inside Qasr Karna, visitors encounter another unexpected feature. Many rooms contain sophisticated vaults and transitional architectural elements known as squinches. These structures transfer loads from square rooms to circular or domed ceilings. Such engineering requires an advanced understanding of force distribution and structural stability. The squinch system was not invented at Qasr Karna. Similar techniques existed in Sasanian Persia and later became common throughout Islamic architecture. Yet their appearance in an early Umayyad monument demonstrates that highly specialized engineering knowledge was already being applied at a remarkably sophisticated level. The builders successfully distributed thousands of kilograms of stone and masonry loads across walls and corners while maintaining structural integrity for more than 13 centuries. Many modern concrete buildings have failed after only a fraction of that lifespan. Qasr Karna still stands. Building a square structure may sound simple. In reality, achieving geometric accuracy across a large construction project is a difficult surveying challenge. The walls of Qasr Karna display impressive alignment and proportional consistency. Builders working in an open desert environment had to establish reference lines, right angles, elevations, and measurements without laser levels, electronic instruments, or modern surveying equipment. Ancient engineers likely relied on ropes, measuring rods, plumb bobs, and geometric techniques inherited from earlier civilizations. The mystery is not whether they could do it. The mystery is how they consistently achieved such accuracy across large projects while leaving almost no documentation of their methods. Perhaps the most debated question concerns the purpose of the structure itself. Several theories compete for acceptance. Some scholars see it as a caravanserai serving travellers along trade routes. Others interpret it as a meeting place for tribal negotiations. Some view it as a rural administrative centre. Others believe it functioned as a temporary residence for elite visitors or members of the Umayyad court. Each theory explains part of the evidence, none explains all of it. The interior layout contains reception spaces suitable for gatherings. The exterior projects authority. The location connects important regional routes, yet the building lacks certain features expected from each proposed function. This ambiguity has transformed Casa Karana into one of the most enigmatic monuments of the early Islamic era. What do you think was Casa Karana's true purpose? A fortress? A diplomatic centre? A caravan station? Or something entirely different? Share your thoughts in the comments below. Yoshinogiri is a vast archaeological site in Saga Prefecture, Kyushu, Japan. More than 2,000 years ago, it became one of the largest and most sophisticated settlements of the Yayoi period. Yet beneath its reconstructed watchtowers and defensive moats lies a mystery that continues to challenge archaeologists today. How did a society with relatively simple tools develop engineering, metallurgy, urban planning, and social organization on a scale that seemed centuries ahead of its time? The modern story of Yoshinogiri began unexpectedly in 1986, when land was being prepared for industrial development. Archaeologists conducting preliminary surveys discovered traces of ancient ditches, post holes, and pottery. What initially appeared to be a routine excavation soon expanded into one of the largest archaeological investigations in Japanese history. Excavations revealed a fortified settlement covering more than 40 hectares, complete with defensive systems, ceremonial structures, elite tombs, workshops, and thousands of artifacts dating primarily between the 3rd century BCE and the 3rd century CE. The discovery transformed understanding of early Japanese civilization. For decades, many historians viewed Yayoi communities as relatively small agricultural villages. Yoshinogiri revealed something very different, displaying evidence of centralized authority, long-distance trade, advanced engineering, and social stratification. More importantly, it exposed several technological mysteries that remain unresolved. The first mystery involves the enormous defensive system surrounding the settlement. Excavations uncovered multiple concentric moats and wooden palisades encircling key areas of the community. Some moats measured several meters wide and deep enough to create significant defensive obstacles. Constructing such fortifications required moving vast quantities of soil using tools made primarily from wood, stone, and limited iron implements. Researchers estimate that excavating even a single large defensive ditch would have required tens of thousands of labor hours. Similar large-scale earthworks are known from Iron Age Europe, including Celtic oppida such as Bibracte in France, and from early Chinese fortified settlements. However, Yoshinogiri demonstrates that comparable organizational capabilities existed in Japan much earlier than previously believed. The question is not whether the moats could be built, because they clearly were. The mystery is how a society without written administrative records coordinated such a massive workforce. Who planned the construction? How was labor organized? How were food supplies managed during major building projects? Archaeologists have found evidence of centralized storage facilities, suggesting some form of political authority, but the exact administrative system remains unknown. The second mystery concerns the enormous wooden towers discovered within the settlement. Archaeologists identified post holes over 1 meter in diameter, indicating that some structures were supported by massive timber columns. Reconstructions suggest that certain towers may have reached heights of 10 to 15 meters. building structures of this scale required far more than simply cutting down trees. Engineers had to select suitable timber, transport heavy logs, excavate stable foundations, and erect columns weighing several tons. Without cranes, steel tools, or modern lifting equipment, the builders achieved remarkable structural stability. Japanese traditional carpentry later became famous for its sophisticated joinery techniques. Some researchers believe Yoshinogari may represent an early stage in the development of these engineering traditions. Yet the precise construction methods remain uncertain, as no detailed instructions survived and the knowledge vanished with the people who created it. The third mystery involves urban planning. Unlike many prehistoric settlements that developed organically, Yoshinogari exhibits signs of deliberate spatial organization. Residential zones, ceremonial areas, workshops, storage facilities, cemeteries, and defensive structures appear carefully arranged. This level of planning resembles development seen in ancient Chinese centers such as Erlitou or early Korean fortified settlements. The arrangement suggests that builders understood concepts of zoning, security, logistics, and social hierarchy. Satellite imagery, aerial surveys, and excavation maps indicate that movement throughout the settlement may have been intentionally controlled through gates, pathways, and enclosed compounds. Such planning implies a sophisticated understanding of social management and security. Yet archaeologists still debate whether these concepts emerged independently within Japan or were influenced by technological and cultural exchanges with mainland Asia. The fourth mystery, and perhaps the most fascinating, involves metallurgy. Yoshinogari has produced numerous bronze and iron artifacts, including weapons, agricultural tools, ritual objects, and mirrors. These discoveries reveal that the community possessed access to some of the most advanced technologies of its era. The transition from stone tools to metal fundamentally changed human history. Iron tools dramatically increased agricultural productivity, while bronze objects became symbols of status, ritual authority, and political power. Control over metallurgy often translated directly into control over society. What makes Yoshinogari remarkable is the speed with which metal technology appears to have spread throughout the region. Bronze mirrors discovered at the site resemble examples found in Han Dynasty China. Certain bronze ceremonial bells, known as dotaku, reflect technological traditions that likely originated on the Asian mainland before being adapted locally. Iron blades and agricultural implements demonstrate knowledge of metalworking that was previously thought to have developed more gradually. The central mystery concerns the source of this knowledge. Did Yoshinogari import finished products from China and Korea? Did immigrant craftsmen bring metallurgical expertise across the sea? Or did local specialists rapidly master foreign technologies and develop their own production systems? Archaeological evidence supports elements of all three possibilities. The distance between northern Kyushu and the Korean peninsula is approximately 200 kilometers at its narrowest crossing. Maritime routes connected these regions long before written Japanese history began. Artifacts discovered at Yoshinogari demonstrate participation in extensive trade networks extending across East Asia. However, trade alone does not explain everything. Several excavations have uncovered evidence suggesting local metalworking activity. Fragments of molds, traces of metal processing, and workshop areas indicate that at least some manufacturing occurred within the settlement itself. Yet complete smelting facilities remain surprisingly scarce. This creates a technological puzzle. Producing bronze requires precise control of copper and tin ratios, while producing usable iron is even more demanding. Iron ore must be heated to temperatures exceeding 1,100 degrees Celsius under carefully controlled conditions. Variations in temperature, oxygen supply, and furnace design can dramatically affect the final product. Even in many parts of Europe, mastering iron production required centuries of experimentation. The Celtic world, the Roman Empire and Han China all invested enormous resources into metallurgical development. How then did a society at the edge of East Asia acquire such capability so rapidly? Some researchers propose that specialized craftsmen migrated directly from the Korean peninsula, carrying technical knowledge with them. Others suggest that technological transfer occurred through generations of trade and cultural interaction. Neither explanation fully accounts for the archaeological evidence. Perhaps the greatest mystery is the disappearance of the knowledge itself. The bronze casters, furnace builders, ore specialists, and metal workers who possessed these skills left behind almost no written explanations. Their products survived, but their methods largely vanished. The fifth mystery concerns the elite cemetery discovered at the site. Hundreds of burials have been excavated, but some individuals received dramatically different treatment than others. Certain graves contain bronze mirrors, weapons, beads, and prestigious imported goods. These burial differences indicate a highly stratified society. This raises another unresolved question. How did social inequality emerge so quickly? For thousands of years, many Jomon communities appear to have maintained relatively egalitarian social structures. Yet, within the Yayoi period, powerful elites emerged who could command labor, control trade, and accumulate wealth. Some archaeologists argue that rice agriculture generated economic surpluses that enabled political centralization. Others believe control over metallurgy and long-distance trade created new power structures. The evidence remains incomplete. Yoshinogiri is often linked to the legendary kingdom of Yamatai, one of Japan's greatest archaeological mysteries. Ancient Chinese records describe Yamatai as a powerful state ruled by Queen Himiko in the 3rd century CE. Because of its large size, strong defenses, elite tombs, and signs of centralized rule, some scholars believe Yoshinogiri may have been a major center of Yamatai. However, no direct evidence confirms this connection, and the true location of Yamatai remains unknown. Ponagar Cham Towers is a 1,000-year-old temple complex overlooking the coast of Nha Trang in central Vietnam. More than a religious monument, it is one of Southeast Asia's greatest engineering mysteries. The towers have survived tropical storms, humidity, salt-laden sea air, and centuries of weathering. Yet many of the construction techniques behind them remain only partially understood. The mystery begins with the bricks. The towers have been known locally for centuries and were documented by European travelers and scholars during the 19th century. Archaeological investigations throughout the 20th century reveal that the surviving structures were built primarily between the 8th and 13th centuries by the Cham civilization, one of the most advanced maritime cultures in Southeast Asia. What researchers expected to find was a typical medieval brick monument. What they found instead was a technological puzzle that remains unsolved. One of the first things visitors notice at Ponagar is the unusual appearance of the brick walls. Unlike many ancient structures where mortar joints are clearly visible, the bricks at Ponagar seem almost fused together. In some sections, the joints are so thin that they are difficult to detect even at close range. For more than a century, archaeologists, engineers, and materials scientists have debated a simple question. How were these bricks joined? Several theories have been proposed. One theory suggests that the Cham builders used an organic adhesive derived from local plant resins. Another proposes that an extremely thin mineral-based mortar was applied and later became nearly indistinguishable from the bricks themselves. A third theory suggests that the bricks may have been partially bonded through heating processes after construction. None of these explanations fully account for all observed evidence. Laboratory analyses have detected traces of organic compounds on some brick surfaces, but no single substance has been identified that could explain the remarkable durability of the joints over 1,000 years. The puzzle becomes even more interesting when Po Nagar is compared with other Cham monuments such as Mai Sun and Poklong Garai. The same construction characteristics appear repeatedly across hundreds of kilometers, suggesting that the builders possessed a standardized technology whose details have largely disappeared from history. Perhaps the most fascinating mystery at Po Nagar concerns the bricks themselves. Modern materials analysis has shown that Cham bricks differ significantly from many contemporary building materials used elsewhere in Southeast Asia during the same period. The bricks display exceptional uniformity, their density is relatively consistent, their porosity appears carefully controlled, and their ability to absorb and release moisture is unusually effective. These characteristics are important because tropical environments are among the most destructive settings for ancient architecture. Moisture enters building materials, expands during temperature changes, promotes biological growth, and gradually weakens structures. Yet many of the bricks at Po Nagar have survived for more than a millennium. Researchers studying the material have noted that the bricks possess a balance between strength and permeability. Rather than completely resisting moisture, they allow water vapor to move through the structure, reducing internal stress and preventing large-scale cracking. This principle resembles concepts employed in some modern conservation materials. The question is how medieval Cham craftsmen achieved such results. Producing high-quality bricks requires control over several variables simultaneously: clay selection, mineral composition, particle size, water content, drying conditions, firing temperature, firing duration, and cooling rate. Even small variations can dramatically affect the final product. Modern industrial brick production relies on laboratory testing, temperature sensors, and precisely controlled kilns. The Cham builders possessed none of these technologies, yet the final results remain impressive. Some materials scientists estimate that firing temperatures may have exceeded 800 to 900 degrees Celsius, while remaining sufficiently controlled to avoid excessive deformation or cracking. The challenge becomes even greater when considering scale. The main tower alone rises more than 20 meters above the ground. Combined with the surrounding structures, the complex required hundreds of thousands of bricks. This raises another mystery. Where were the production facilities? Archaeologists have not discovered kiln complexes large enough to explain the enormous quantity of material used in major Cham construction projects. If massive industrial-scale brick production existed, much of the evidence has either disappeared or remains undiscovered. Comparisons with other ancient civilizations make the achievement even more remarkable. Roman builders became famous for concrete. The Maya mastered limestone construction. The Khmer Empire developed sophisticated sandstone architecture at Angkor. The Cham civilization appears to have specialized in advanced fired brick technology, yet unlike Roman concrete, whose composition can be studied directly, crucial aspects of Cham brick production remain uncertain. Po Nagar stands only a short distance from the sea. Marine environments are notoriously destructive. Salt carried by wind penetrates building materials and accelerates deterioration. Tropical storms generate extreme rainfall and powerful winds. High humidity encourages biological growth. Many modern reinforced concrete structures require significant maintenance under similar conditions. Yet Po Nagar has remained standing for centuries. Engineers studying the towers have identified several features that may have contributed to their longevity. The walls are exceptionally thick. The towers taper gradually toward the top. Weight is distributed vertically through massive structural cores, and openings are limited and strategically positioned. Together, these characteristics create a highly stable structure capable of resisting environmental stress. The design demonstrates an understanding of load distribution that appears remarkably sophisticated for the period. Although the towers are primarily constructed from brick, important architectural and religious elements were carved from stone. The most famous example is the statue of the goddess Yan Po Nagar, originally one of the most significant sacred objects in the complex. Some stone components weigh several tons. Transporting such materials presented major logistical challenges. The Cham builders had no cranes, hydraulic lifts, or modern transportation systems, yet they successfully integrated heavy stone elements into elevated architectural settings. How they accomplished this remains uncertain. Researchers generally assume the use of ramps, rollers, ropes, and coordinated labor forces, but direct archaeological evidence is limited. The problem resembles questions asked at Borobudur in Indonesia and Angkor Wat in Cambodia. The monuments survive. The precise construction procedures remain largely unknown. One of the most remarkable aspects of Ponagar is simply that it still exists. More than 1,000 years of environmental exposure should have produced far greater damage. Instead, the towers continue to dominate the landscape. Their survival suggests that Cham builders understood principles of structural stability through generations of accumulated experience. Without formal engineering equations, computer simulations, or modern mathematics, they developed architectural solutions that proved effective over centuries. This knowledge was likely transmitted through apprenticeships and practical training. Unfortunately, very little written technical documentation survives. The buildings remain, the engineering manuals do not. In the Judean desert near the Dead Sea, a 5,500-year-old temple stands beside a spring. No palace surrounds it, no city protects it. Yet the people who built it may have possessed engineering knowledge far beyond what archaeologists once thought possible. The site, now known as the Ein-Gedi Chalcolithic Temple, was excavated during the 1960s by archaeologist Benjamin Mazar and his team. Radiocarbon dating placed the sanctuary within the Chalcolithic period, approximately 3,500 to 3,700 BCE. What appeared at first to be a small desert shrine soon became one of the greatest mysteries of prehistoric engineering in the Near East. The first mystery begins with the temple's very existence. Most ancient temples are found within settlements. Egyptian temples stood beside cities, Mesopotamian temples formed the heart of urban centres, and even prehistoric ceremonial sites such as Göbekli Tepe were associated with communities that supported their construction. Ein-Gedi is different. Archaeologists found a carefully planned sanctuary, but no large settlement capable of supporting such a project. The temple consists of a courtyard, stone walls, ceremonial structures, and a distinctive altar, all suggesting organised construction and long-term use. Yet the population centre responsible for building and maintaining the complex remains largely unknown. This creates a logistical puzzle. Even a modest temple requires labour, food supplies, planning, transportation of materials, and specialised knowledge. Hundreds of workers may have participated in construction and maintenance over many years. Where did they live? How was labour organised? Who directed the project? More than half a century after excavation began, the answers remain elusive. One of the least discussed but most significant mysteries involves surveying. The temple was not randomly assembled. Its structures follow a coherent plan, walls align with specific spatial relationships, and open areas connect logically to ritual spaces. The sanctuary appears designed rather than gradually accumulated. This is remarkable because the temple predates many of the sophisticated surveying traditions associated with later civilizations. Today, surveyors use laser equipment, GPS systems, and digital mapping. Ancient Egyptian engineers used ropes, measuring rods, and astronomical observations. The builders of Ein-Gedi had none of these documented tools, yet they successfully established a stable architectural layout within a difficult desert environment. Researchers still debate how Chalcolithic builders measured distances, established straight lines, and maintained consistency during construction. No written manuals survive, and no measuring instruments have been identified with certainty. Whatever methods were used, the knowledge appears to have vanished completely. The location of the temple may reveal another lost technology. Ein Gedi is an oasis where fresh water emerges from springs fed by underground geological systems beneath one of the driest regions in the Middle East. The temple was deliberately positioned near this water source. At first glance, this may seem obvious, since human settlements often develop near water, but the precision of the site's placement raises important questions. The builders selected one of the most reliable freshwater locations in the region and understood where water would remain available despite seasonal changes and harsh environmental conditions. Modern hydrogeologists use geological mapping, groundwater modeling, and remote sensing technologies to understand aquifers. How people living more than 5,500 years ago identified and exploited such a favorable location remains uncertain. Some researchers believe generations of environmental observation allowed them to recognize underground water patterns, while others suggest sophisticated local knowledge accumulated over centuries. Whatever the explanation, the builders demonstrated an understanding of landscape resources far beyond simple survival. The temple also presents questions about prehistoric construction methods. Unlike later civilizations that used large-scale masonry blocks, Chalcolithic builders worked with local stone resources. The challenge was not merely obtaining stone, but constructing durable structures capable of surviving harsh desert conditions. Summer temperatures regularly exceed 40 degrees Celsius. Seasonal floods occasionally sweep through nearby valleys, and earthquakes have affected the region throughout history. Despite these challenges, portions of the sanctuary survived for millennia. The builders selected suitable stone, created stable foundations, and developed construction methods that resisted environmental stress. Modern engineers understand how temperature fluctuations create expansion and contraction cycles that gradually weaken structures, yet many elements of the sanctuary endured for more than 5,000 years. This suggests a practical understanding of materials and structural stability that remains difficult to reconstruct today. At the heart of the sanctuary stands one of its most famous features, a crescent-shaped altar. The object immediately stands out because of its unusual form and careful proportions. Creating a symmetrical curved structure without modern drafting tools requires planning, measurement, and geometric understanding. Similar challenges confronted builders at sites such as Stonehenge and Newgrange, where geometry appears embedded within ceremonial architecture. The altar raises fundamental questions. Did the builders possess formal geometric principles? Were proportions transmitted through apprenticeships? Did ritual specialists preserve mathematical knowledge through oral tradition? Because the Chalcolithic culture left no written records explaining its construction methods, archaeologists can only speculate. The altar remains a silent demonstration of knowledge whose origins have been lost. This is the most extraordinary mystery associated with Ein Gedi. In 1961, explorers discovered a hidden cache inside a cave near a Nahal Mishmar, approximately 12 kilometers from the temple. The discovery stunned archaeologists. More than 400 artifacts were found carefully wrapped and concealed, including ceremonial staffs, crowns, scepters, standards, mace heads, and complex copper objects unlike anything previously known from the region. The cache became known as the Nahal Mishmar Hoard. Many scholars believe these artifacts may have originated from the Ein Gedi temple. If true, the implications are astonishing. The artifacts demonstrate an advanced metallurgical tradition during a period often viewed as technologically primitive. Several objects were produced using lost wax casting, one of the most sophisticated metalworking techniques in human history. Lost wax casting requires creating a wax model, covering it with clay, heating the mold to remove the wax, and pouring molten metal into the cavity. The process demands precise temperature control and extensive technical knowledge, and even minor mistakes can ruin the entire casting. Some Nahal Mishmar artifacts contain extraordinarily complex shapes that would challenge inexperienced metalworkers even today. Researchers have calculated that copper must be heated to approximately 1085 degrees Celsius before melting. Achieving and maintaining such temperatures requires carefully designed furnaces, controlled airflow, high-quality fuel, and skilled operators. This raises a critical question. Where did this knowledge come from? The technology appears surprisingly advanced compared with many contemporary societies. When compared with other Chalcolithic sites throughout the Near East, the craftsmanship of the Nahal Mishmar object stands out dramatically. Some scholars describe the collection as representing one of the earliest known examples of specialized industrial production. The mystery becomes even deeper because the artisans themselves vanished from history. No workshop has been definitively identified, no technical manuals survive, and no written descriptions explain the manufacturing process. Only the artifacts remain. If the hoard truly belonged to the temple, then Ein Gedi was not merely a religious center. It may have been part of a technological network capable of producing some of the most sophisticated metal objects on Earth during the 4th millennium BCE. Every ancient monument ultimately leads to the same question: who built it? The society responsible for Ein Gedi appears far more organized than earlier models of prehistoric communities suggested. Construction required planning, religious ceremonies required coordination, metallurgical production required specialists, and trade networks supplied raw materials. The copper used in some Chalcolithic artifacts likely originated hundreds of kilometers away, implying long-distance exchange systems operating across large regions of the Near East. Such complexity resembles the organizational capabilities later associated with early states. Yet no king is known, no royal inscriptions exist, and no administrative archives survive. The people responsible remain anonymous. Misrian, hidden within the abandoned Dahistan oasis of western Turkmenistan, should never have existed. Surrounded by arid lands and harsh climatic conditions, this medieval city once supported thousands of inhabitants. Monumental architecture, industrial-scale construction, and a sophisticated water network. Today, only ruins remain. Yet the greatest mystery is not why the city vanished, but how it was built in the first place. The ruins of Misrian attracted the attention of Russian explorers during the 19th century. Systematic archaeological investigations expanded throughout the 20th century, revealing the remains of a major urban center that flourished between the 10th and 14th centuries. Excavations uncovered massive fortifications, industrial workshops, mosques, water systems, and 2 extraordinary towers that continue to stand nearly 1,000 years after their construction. The greatest challenge facing Misrian's builders was obvious: water. The Dahistan region receives only a small amount of annual rainfall. Modern climatological studies indicate precipitation levels often remain below 150 millimeters per year, a figure comparable to many semi-arid environments across Central Asia. Under such conditions, sustaining a large urban population would be impossible without advanced hydraulic engineering. Yet archaeological surveys have identified traces of extensive irrigation networks connecting settlements throughout the Dahistan oasis. These canals transformed otherwise inhospitable land into productive agricultural territory capable of supporting large populations. The mystery lies in the precision required to make such a system function. Water channels extending for many kilometers must maintain carefully controlled gradients. A slope that is too steep causes erosion and structural failure, while a slope that is too shallow prevents water from flowing effectively. Modern irrigation engineers use surveying equipment, satellite data, and computer modeling to achieve such precision. The engineers of Misrian possessed none of these technologies. How did they calculate gradients across vast distances? How did they map terrain hidden beneath seasonal vegetation and shifting sediments? What surveying instruments allowed them to maintain hydraulic efficiency over an entire oasis? The surviving evidence demonstrates that they succeeded, but the methods remain largely unknown. Comparable challenges can be seen in the Qanat systems of ancient Persia and the irrigation networks of Merv, another major Silk Road city. Yet many details of Dahistan's hydraulic engineering remain less understood than those famous examples. Excavations have revealed evidence of more than 100 brick production facilities across the region. This discovery transformed archaeologists' understanding of Misrian. Rather than a modest oasis settlement, the city appears to have functioned as a major manufacturing center, capable of producing enormous quantities of building materials. Massive walls, religious complexes, towers, public buildings, and residential districts required millions of bricks. Producing such quantities presents serious engineering questions. Brick kilns must reach temperatures often exceeding 800 to 1000 degrees Celsius. Maintaining these temperatures consistently requires fuel, airflow control, labor organization, and standardized production methods. The environmental puzzle is particularly intriguing. Where did the fuel come from? Today, the surrounding landscape offers limited vegetation. Researchers suggest that climatic conditions may have been somewhat different during the city's peak, but the scale of brick production implies a supply chain operating for generations. The situation resembles challenges faced by builders in ancient Mesopotamia, where large cities consumed enormous quantities of fuel to manufacture construction materials. Yet, unlike Mesopotamia, Misrian existed within a more environmentally fragile setting. Its continued growth suggests a surprisingly sophisticated system of resource management. Many medieval cities struggled with sanitation. Waste accumulation, contaminated water, and poor drainage frequently contributed to disease outbreaks. Even some major European cities of the High Middle Ages lacked effective urban sanitation systems. Misrian appears to have been different. Archaeological investigations have identified drainage systems, water management features, and public infrastructure associated with urban planning. These discoveries suggest that city planners understood principles of water control extending beyond irrigation. Managing water in a desert environment requires balancing two opposite problems simultaneously. Too little water threatens survival, while too much water in concentrated areas damages foundations and infrastructure. The builders appear to have designed systems capable of handling both challenges. This raises another unanswered question. Was this knowledge developed locally, imported through Silk Road connections, or inherited from earlier Central Asian engineering traditions? The answer remains uncertain. Among all the mysteries of Misrian, none is more remarkable than the survival of its two monumental towers. Nearly every city eventually succumbs to time. Walls collapse, roofs disappear, earthquakes destroy foundations, and wind erodes exposed surfaces. Yet the towers of Misrian continue to stand. The most famous structure is associated with Abu Jafar Ahmed, dating to approximately the early 11th century. Rising above the surrounding ruins, the tower remains one of the most impressive surviving monuments in Western Turkmenistan. From an engineering perspective, its survival is astonishing. For nearly 1,000 years, the structure has endured relentless environmental stress. Seasonal temperature fluctuations expand and contract construction materials. Wind-driven sand acts like natural sandpaper, slowly eroding exposed surfaces. Occasional seismic activity affects structural stability, and rainwater penetrates cracks and weakens mortar. Despite these forces, the tower remains standing. Why? Researchers point towards several possibilities. The first involves geometry. Cylindrical structures distribute stress more evenly than many rectangular buildings. Similar principles explain why ancient Roman towers, Islamic minarets, and certain lighthouse designs often survive longer than surrounding structures. The second possibility involves materials. The bricks appear to have been manufactured to unusually high standards. Uniform firing temperatures produce stronger ceramic structures with greater resistance to weathering. Some analyses suggest that medieval Central Asian brickmakers achieved impressive consistency and production quality. The third possibility concerns mortar technology. Throughout history, durable construction has often depended less on stone or brick and more on the material holding them together. Roman concrete remains famous because some marine structures have survived for nearly 2,000 years. Medieval builders throughout Central Asia developed sophisticated mortar mixtures adapted to local environmental conditions. The exact composition used in Misrian's towers remains a subject of ongoing investigation. The fourth possibility involves foundation engineering. A structure can only survive if its foundation distributes weight effectively across the ground below. Archaeologists continue studying how the builders prepared the subsurface layers supporting these monuments. What makes the mystery even more fascinating is comparison. Many modern reinforced concrete structures are designed with service lives of approximately 50 to 100 years before major rehabilitation becomes necessary. The towers of Misrian have already exceeded that lifespan by nearly an order of magnitude. Their survival represents not merely architectural achievement, but a demonstration of engineering knowledge whose full details may have been lost. Perhaps the greatest mystery is why Misrian disappeared. Evidence suggests the city did not fall to a single invasion or battle, but declined as the oasis systems that supported it gradually failed. As irrigation networks deteriorated, agriculture weakened, populations shrank, and maintaining infrastructure became increasingly difficult. This likely created a cycle of decline, a pattern seen in other irrigation-based societies throughout history. Many questions remain. Was climate change responsible? Did rivers change course? Were resources overused? Or did political instability disrupt maintenance? The evidence is still incomplete. Oshoro Stone Circle on the western coast of Hokkaido, Japan, appears at first glance to be nothing more than a ring of scattered stones. Yet more than 3,000 years ago, people with no metal tools, no written language, and no wheeled transportation created a monument whose geometry still raises questions that modern archaeology cannot fully answer. The site was first reported in the 19th century near Oshoro Bay. Later, archaeological investigations identified it as a ceremonial stone circle dating to the late Jomon period, roughly between 2500 and 1000 BC. What researchers expected to be a simple prehistoric ritual site gradually revealed evidence of surprisingly sophisticated planning. Among all the unanswered questions surrounding Oshoro, none is more intriguing than its geometry. Creating a circular monument sounds simple today. A surveyor can establish a center point, use measuring tapes, GPS equipment, laser levels, and digital mapping software. But the builders of Oshoro possessed none of these technologies. The Jomon people lived thousands of years before the introduction of iron tools into Japan. Their technology was based largely on stone, bone, wood, fibre and clay. Yet the arrangement of stones suggests that the builders understood concepts of spatial planning that required far more than a random placement. Archaeologists studying stone circles around northern Japan have repeatedly noted evidence of deliberate geometric organization. The stones were not simply dropped where they happened to fall. They were positioned according to a plan. The challenge is understanding how that plan was created. One possibility is that Yuman surveyors used ropes made from plant fibers. By fixing a central stake and extending a rope of constant length, they could theoretically produce a circular layout similar to the method used by many ancient civilizations. The principle is simple, but the execution is not. Even a small error in the position of the center point can distort an entire circle. Maintaining accuracy across dozens of stones requires repeated measurements and careful verification. Modern experiments demonstrate how difficult this can be. Experimental archaeologists attempting to recreate prehistoric circles often find that tiny deviations accumulate quickly. A mistake of only a few centimeters at the beginning can become a major misalignment by the end of construction. Yet many ancient stone circles display remarkable consistency. This raises a fascinating possibility. Were specialized surveyors operating within Jomon society? The traditional image of Yuman communities portrays them as small groups of hunter-gatherers. However, monuments such as Ashoro suggest the existence of individuals who possessed advanced practical knowledge of measurement and planning. No measuring tools have been found. No written instructions survive. No records explain the process. The geometry remains, but the knowledge behind it has vanished. The mystery becomes even more compelling when compared with other prehistoric monuments. Stonehenge in England demonstrates geometric planning around 2500 BC. The ring structures of Nabta Playa in Egypt date even earlier. Across Europe, dozens of Neolithic circles reveal similar organizational principles. Yet the builders of Ashoro lived on the opposite side of the world with no known contact with those cultures. Why did societies separated by thousands of kilometers independently develop circular stone architecture? Was the circle simply the most practical geometric form available to prehistoric engineers? Or does its repeated appearance suggest a deeper understanding of space, ritual, and landscape? No definitive answer exists. Building the circle required more than geometric planning. The stones had to be moved. This is where another technological mystery emerges. The late Jomon period predates the widespread use of wheeled transportation in Japan. There is no evidence that the builders possessed carts, draft animals, or advanced lifting machinery. Yet the stones did not transport themselves. Researchers studying Jomon stone circles elsewhere in northern Japan have discovered that many stones originated from riverbeds located several kilometers away. Similar transportation challenges may have existed at Ashoro. Even a stone weighing only 100 kilograms presents significant logistical difficulties when moved over uneven terrain. A stone weighing several hundred kilograms becomes exponentially more difficult. Experimental studies suggest that teams using ropes, wooden sledges and rollers can move surprisingly large loads. However, such operations require planning, manpower, coordination, and leadership. The engineering challenge resembles those faced at other ancient sites. The builders of Stonehenge transported some bluestones more than 200 kilometers. The craters of Easter Island's Moai moved statues weighing up to 80 tons. The ancient Egyptians moved limestone blocks weighing several tons for pyramid construction. Ashoro operated on a smaller scale, but the underlying problem was identical. How do people without modern machinery move heavy materials accurately and repeatedly? The answer remains uncertain. Another debate centers on the purpose of the monument. Most archaeologists interpret Ashoro as a ceremonial and funerary site. This conclusion is supported by comparisons with other Jomon stone circles, where burials and ritual deposits have been discovered. However, the story may be more complicated. Several famous Jomon stone circles, including those at Oyu and Isidatai, display alignments associated with solar events such as sunrise and sunset during solstices. Researchers have proposed that these monuments functioned as seasonal markers. For societies dependent on fishing, gathering, hunting, and plant harvesting, understanding seasonal cycles was essential. A difference of only a few weeks could determine the success or failure of food collection activities. Tracking the movement of the sun provided valuable environmental information. Could a Shoro have served a similar role? If so, the builders possessed a practical knowledge of observational astronomy that has left little direct evidence behind. This possibility transforms the monument from a simple ritual space into a prehistoric information system. Not a telescope, not an observatory in the modern sense, but a carefully designed structure capable of encoding environmental knowledge into stone. Perhaps the most revolutionary question concerns social organization. For decades, archaeologists assumed that large-scale monument construction required agriculture, social hierarchy, and centralized authority. Sites like Ashoro challenge that assumption. The Jomon people were not farmers on the scale of ancient Mesopotamia or Egypt, yet they created pottery among the oldest in the world, established long-term settlements, and constructed ceremonial monuments. Building a stone circle requires collective labor. Workers must gather materials, surveyors must plan layouts, communities must provide food for participants, leaders must coordinate activities. None of this happened spontaneously. The existence of Ashoro suggests a level of social complexity far beyond what researchers once attributed to prehistoric hunter-gatherers. This realization has forced archaeologists to reconsider long-standing theories about how civilization develops. Golubak Fortress is one of the most strategically positioned fortresses ever built in medieval Europe. Standing on the right bank of the Danube River in eastern Serbia, at the entrance to the Iron Gates Gorge, the fortress occupies a location where geography, engineering, and military architecture converge in ways that still challenge modern understanding. For centuries, armies fought to control it, empires rebuilt it, and engineers modified it. Yet some of the knowledge that made its construction possible remains surprisingly difficult to explain. The fortress dominates a narrow section of the Danube where the river begins its transition into the Iron Gates, one of Europe's largest river gorges. Today, visitors see 10 towers rising above steep limestone cliffs, but the most fascinating story is not what survives. It is how medieval builders managed to construct, reinforce, and maintain such a complex defensive system on terrain that appears almost impossible for large-scale construction. The existence of Golubak was documented in medieval records beginning in the 14th century, although archaeological evidence suggests earlier fortifications may have occupied the site long before the fortress reached its final form. Excavations, restoration projects, geological surveys, and modern laser scanning have revealed numerous construction phases associated with Serbian, Hungarian, and Ottoman control. Yet every new discovery seems to generate additional questions about the engineering capabilities of its builders. The first mystery concerns the fortress's location itself. Many medieval castles were built on hills, but Golubak occupies a far more difficult environment. Portions of the fortress rise directly from limestone cliffs overlooking the Danube, and some towers stand on slopes approaching angles that would challenge modern construction equipment. Engineers today rely on cranes, reinforced concrete foundations, geotechnical drilling, and computer simulations when building on similar terrain, but medieval builders possessed none of these technologies. Researchers estimate that thousands of tons of stone were transported and positioned during construction and expansion phases, yet the exact methods remain unknown. Historical records provide no detailed construction manuals, and no contemporary blueprints survive. Nevertheless, the fortress demonstrates remarkable adaptation to natural topography. Rather than forcing the landscape to conform to a standard design, builders integrated walls, towers, and defensive positions directly into the existing rock formations. This suggests a sophisticated understanding of structural stability. The builders appear to have recognized which sections of bedrock could support heavy masonry and which areas required reinforcement. Such knowledge normally develops through generations of accumulated practical experience. But the challenge is that very little documentation survives explaining how that knowledge was transmitted. The second mystery involves the unusual tower system. Golubac contains 10 primary towers, but unlike many medieval fortifications, they are not uniform in shape. Some towers are square, others are polygonal, and several display evidence of major modifications. Historians traditionally explained these differences as the result of construction occurring over multiple centuries. While this is undoubtedly true, modern architectural analysis suggests something more complex. The positioning of certain towers appears optimized for overlapping fields of fire and observation. Their arrangement takes advantage of natural blind spots created by the terrain, and in several cases, the shape of a tower may have been influenced by local geological conditions rather than purely military considerations. This raises an important question. How sophisticated were medieval surveyors working at Golubac? Modern topographic studies indicate that even small errors in tower placement could have created defensive weaknesses. Yet the fortress maintained effective coverage across critical approaches from both land and river. Achieving such precision without modern surveying instruments remains an impressive accomplishment. The third mystery centers on the Danube itself. Golubac was not merely a fortress, it was also a mechanism for controlling one of Europe's most important transportation corridors. Historical sources describe the existence of a massive chain stretched across the Danube near the fortress. Similar systems existed elsewhere in medieval Europe, but Golubac's location made such a barrier particularly effective. The river narrows significantly before entering the Iron Gate's gorge, creating a natural choke point for commercial and military traffic. The engineering challenges associated with this system are rarely discussed. The Danube is Europe's second longest river, extending approximately 2,850 kilometers. Its flow can exert enormous force on any obstacle placed across its channel. A chain capable of stopping ships would require advanced ironworking techniques, secure anchoring systems, and mechanisms for raising and lowering enormous weights. No complete remains of this system survive. Consequently, historians still debate exactly how it functioned. Was the chain permanently installed or deployed only during emergencies? How were its anchor points reinforced? What mechanical systems assisted operators? These questions remain largely unanswered. The fourth mystery, and perhaps the most overlooked, is the technology behind the fortress's mortar. When visitors look at Golubac, they naturally focus on the towers and walls. Yet the true secret of the fortress may lie in the material holding those stones together. Mortar is often treated as a secondary component in ancient and medieval construction. In reality, it frequently determines whether a structure survives for centuries or collapses within decades. Golubac has endured earthquakes, warfare, seasonal flooding, extreme temperature fluctuations, moisture infiltration, biological growth, and continuous exposure to wind coming through the Danube corridor. Despite these conditions, significant portions of the masonry remain intact. Materials scientists studying historic structures have repeatedly discovered that ancient builders sometimes produced mortars with properties that are difficult to replicate precisely today. The Roman Empire provides perhaps the most famous example. Roman marine concrete has survived for nearly 2,000 years in aggressive coastal environments, while many modern concretes deteriorate far more quickly. Analysis revealed that volcanic ash, lime, and complex chemical reactions contributed to the material's extraordinary durability. Golubac presents a similar puzzle on a smaller scale. Laboratory studies of medieval mortars across the Balkans have shown that builders often combined lime with carefully selected aggregates and occasionally organic additives. Animal products, plant fibers, charcoal particles, brick dust, and other ingredients have been identified in historical mortars from various regions. The exact composition used at Golubac likely varied across different construction phases, but researchers continue investigating why some sections have survived exceptionally well despite centuries of environmental stress. One possibility is that local builders possess practical knowledge of limestone chemistry that was never formally documented. Another possibility is that generations of craftsmen refined mortar recipes through trial and error, gradually developing mixtures optimized for local climate conditions. The problem is that this knowledge was transmitted through apprenticeship rather than written technical manuals. When political systems changed, wars disrupted communities, or skilled craftsmen disappeared, much of that expertise vanished as well. The result is a paradox. Modern scientists can analyze surviving mortar at microscopic and chemical levels. They can identify minerals, measure porosity, examine crystal structures, and reconstruct manufacturing processes. Yet they still cannot fully recreate the cultural knowledge system that produced the material in the first place. The fifth mystery involves adaptation to gunpowder warfare. Golubac occupied a strategic frontier during the period when artillery was transforming military architecture across Europe and the Ottoman world. Many medieval castles became obsolete after the widespread introduction of cannons. High vertical walls that resisted arrows and siege engines proved vulnerable to concentrated artillery fire, and fortifications throughout Europe underwent major redesigns. Golubac demonstrates evidence of this transition. Certain towers were reinforced, wall thicknesses increased in some areas, and defensive layouts evolved to accommodate firearms and artillery. What fascinates historians is the speed with which these adaptations occurred. The fortress appears to have undergone continuous technical evolution as military technology changed, suggesting access to skilled engineers capable of understanding emerging threats and modifying existing structures accordingly. The sixth mystery concerns water management. Every major fortress requires a reliable water supply, and during a siege, access to water often determined survival. Golubac stood beside the Danube, yet proximity to a river does not guarantee security. Defenders needed protected access to water even when enemy forces controlled surrounding territory. Archaeological evidence indicates the presence of cisterns and water storage systems, but researchers continue debating how the fortress maintained long-term water security. Were hidden passages used to reach the river? Did engineers create sophisticated rainwater collection systems? Or were there additional hydraulic features that have yet to be discovered? The answers remain uncertain. Rabat Malik stands among the great engineering enigmas of the Silk Road. Located on the arid plains of present-day Uzbekistan between Bukhara and Samarkand, its ruins seem modest at first glance. Yet nearly 1,000 years ago, this complex ranked among the most sophisticated structures in Central Asia. Archaeologists have uncovered massive fortifications, monumental gateways, advanced hydraulic systems, and architectural features that continue to puzzle researchers. Despite decades of excavation, scholars still debate its true purpose, the construction techniques behind it, and how its builders created a self-sustaining complex in one of the harshest environments along the Silk Road. The story of Rabat Malik began not with ancient texts, but with ruins visible to travelers crossing Central Asia. Russian explorers and scholars documented the surviving gateway during the 19th century, while major archaeological investigations throughout the 20th century gradually revealed the buried remains of a much larger complex. Excavations showed that the site was not merely a roadside caravanserai. Beneath the sands lay evidence of a fortified royal residence, extensive courtyards, service buildings, water infrastructure, and defensive walls covering thousands of square meters. Every new discovery raised more questions than answers. The first mystery concerns the true function of Rabat Malik. Historical sources generally describe it as a caravanserai, a stopping point for merchants traveling between the great cities of Transoxiana. Yet the architecture suggests something far more complex. The complex occupied an area estimated at over 8,000 square meters. Its monumental entrance featured elaborate geometric decoration, intricate brickwork, and structural sophistication rarely found in ordinary commercial facilities. Archaeologists discovered evidence of multiple courtyards, residential sections, religious spaces, and administrative areas. Comparisons with other Silk Road caravanserais reveal significant differences. Many caravanserais were designed primarily for protection and accommodation. Rabat Malik, however, displays characteristics associated with elite architecture. Some researchers believe it may have served as a royal palace for Karakhanid rulers before later being converted into a caravanserai. Others argue that it functioned as both a palace and a strategic trade station simultaneously. This uncertainty creates a fascinating paradox. If Rabat Malik was only a caravanserai, why was it built on such an extraordinary scale? If it was a palace, why was it located in the middle of a semi-arid steppe far from major urban centres? Nearly a millennium later, scholars still disagree. The second mystery, and perhaps the most remarkable technological puzzle, is the water supply system hidden beneath the dry steppe. Today, the landscape surrounding Rabat Malik appears unforgiving. Annual precipitation in much of the region is relatively low, and summer temperatures frequently exceed 40 degrees Celsius. Sustaining hundreds of travelers, animals, servants, guards, and residents would have required a reliable water source throughout the year. Yet archaeological evidence indicates that Rabat Malik possessed exactly such a system. Researchers discovered ceramic pipelines, underground channels, storage facilities, and connections to one of Central Asia's most impressive hydraulic structures, the Sardoba Malik Reservoir. Located near the complex, the Sardoba is a massive domed water storage system approximately 13 meters high and more than 15 meters in diameter. The structure was designed to collect, preserve, and protect water from evaporation under extreme climatic conditions. What makes this system extraordinary is not simply its size, but the engineering knowledge required to make it function. Transporting water across long distances without modern pumps requires precise control of gradient. Even a slight error in elevation can prevent water flow entirely or create destructive pressure within channels. Modern engineers use laser surveying equipment, GPS systems, and digital terrain models to calculate such gradients. The builders of Rabat Malik relied on none of these technologies. How did they determine elevation differences across kilometers of open terrain? How did they maintain consistent flow rates? How did they prevent contamination and sediment buildup? These questions remain only partially answered. The challenge becomes even more impressive when compared to other ancient hydraulic systems. Roman aqueducts relied on carefully calculated gradients, averaging only a few centimeters per 100 meters. Persian qanats transported groundwater across deserts through underground tunnels extending for dozens of kilometers. The engineers of Rabat Malik appear to have applied similar principles in a Silk Road environment, where water management meant the difference between survival and abandonment. Some archaeologists argue that the hydraulic network represents inherited engineering traditions stretching back centuries through Persian, Sogdian, and Islamic civilizations. Others suggest local innovations adapted specifically for Central Asian conditions. Regardless of origin, the system demonstrates a level of environmental engineering that remains astonishing today. The third mystery involves the fortress-like design of the complex. Excavations revealed defensive walls, towers, controlled entry points, and a layout emphasizing security. The surviving gateway alone suggests a structure intended to project authority and withstand attack. Historical reconstructions indicate walls reaching considerable heights and enclosing large internal spaces. This raises an obvious question. Why would a roadside accommodation facility require military-grade defences? The answer may lie in the strategic importance of the Silk Road. During the 11th and 12th centuries, trade routes carried silk, spices, precious metals, ceramics, scientific knowledge, and diplomatic missions across Eurasia. Controlling these routes meant controlling wealth. Rabat Malik occupied a critical position between two of Central Asia's greatest cities, Bukhara and Samarkand. Any power seeking to monitor commerce, collect taxes, protect travellers, or project political influence would have benefited from maintaining a strong presence at this location. Yet the scale of fortifications still appears excessive. Some researchers believe the structure served as a strategic royal outpost capable of housing military personnel alongside travellers. Others suggest that its defensive architecture reflected broader political instability during the Karakhanid period. The fourth mystery centers on construction technology. The surviving entrance of Rabat Malik is considered one of the masterpieces of Karakhanid architecture. The gateway incorporates complex geometric patterns, decorative brickwork, structural arches, and carefully engineered load distribution systems. Unlike simple masonry construction, monumental gateways must transfer enormous forces around openings while preventing collapse. Every brick contributes both decorative and structural functions. Modern structural analysis shows that such systems require sophisticated understanding of compression forces, material behavior, and geometric stability. What makes Rabat Malik particularly intriguing is the precision achieved using relatively simple materials. Builders relied primarily on fired bricks, clay mortars, and gypsum-based binding materials. Yet portions of the structure survived earthquakes, climate extremes, and centuries of neglect. Comparisons with contemporary Islamic architecture reveal similar innovations in cities such as Bukhara, Merv, and Samarkand. However, Rabat Malik remains unique because it combines monumental ceremonial architecture with practical frontier engineering. The fifth mystery concerns logistics. Constructing a complex of this scale required enormous resources. Thousands of tons of bricks had to be manufactured, transported, and assembled. Water systems required excavation and maintenance. Decorative elements demanded skilled artisans. Food and supplies had to support large workforces throughout construction. Modern estimates suggest that projects of comparable scale would require hundreds of labourers working for years. Organising such efforts demands administration, planning, surveying, and resource management. Yet almost nothing is known about the engineers who directed these operations. No construction manuals survive. No technical drawings have been discovered. No detailed descriptions explain how the project was organised. The builders left behind the results of their expertise, but almost none of the knowledge itself. Perhaps this is the greatest mystery of all. Sudak Fortress is a medieval giant standing on a volcanic hill above the Black Sea coast of Crimea. More than 6 centuries after its construction, its walls still dominate the landscape. Yet the greatest mystery is not the fortress itself. It is how medieval engineers, working without modern surveying instruments, cranes, or scientific materials laboratories, created a defensive system so durable that large portions remain standing today. The fortress was never truly lost. Historical records from Genoese merchants described Sudak as one of the most important trading and military centres of the northern Black Sea. Archaeological investigations beginning in the 19th century and continuing through the 20th and 21st centuries revealed the complex engineering hidden within its walls, towers, water systems, and construction materials. Sudak Fortress occupies a volcanic rock formation, rising approximately 157 meters above sea level. The position appears almost perfectly engineered by nature itself. Steep cliffs protect 3 sides of the hill, leaving only a limited approach for attackers. Military historians often compare strategic locations like Sudak to famous strongholds such as Masada or Crac de Chevalier. Yet Sudak possessed an additional advantage. It overlooked major maritime trade routes connecting the Byzantine Empire, the Caucasus, Central Asia, and the Mediterranean. What remains unclear is how medieval surveyors evaluated the site so effectively. Without aerial photography, satellite imagery, or topographic mapping, they identified a location that maximized visibility, controlled trade routes, and minimized defensive vulnerabilities. Modern geographic information system analysis demonstrates that observers from the fortress could monitor vast sections of the surrounding coastline and see approaches. Such strategic optimization suggests a level of geographic knowledge far beyond what many people associate with the medieval period. Most people imagine a fortress as a single wall surrounding a settlement. Sudak was something entirely different. The fortress was organized into multiple defensive zones. Attackers who breached the outer walls still faced additional layers of fortification. The system functioned much like a modern defense-in-depth strategy, forcing enemies to fight uphill through successive barriers. The outer defensive circuit stretched for nearly 2 kilometers and incorporated more than a dozen towers. Each tower was positioned to support neighboring towers through overlapping fields of fire. Archers and crossbowmen could cover areas that would otherwise become vulnerable blind spots. Computer simulations performed on medieval fortifications show that overlapping defensive coverage dramatically increases survival rates during sieges. Yet the exact methods used by Genoese engineers to calculate these relationships remain unknown. There are no surviving blueprints. There are no surviving engineering manuals. The fortress itself is the only surviving evidence of the calculations. One of the least discussed mysteries involves measurement. The walls follow the irregular contours of the mountain while maintaining structural stability over long distances. Achieving this required accurate surveying. Modern engineers use laser scanners capable of measuring distances to within millimeters. Medieval builders relied on ropes, plumb lines, wooden levels, and geometric principles inherited from Roman and Byzantine traditions. The question is not whether these tools existed. The question is how such simple instruments produced results accurate enough to construct a fortress across steep volcanic terrain. Archaeologists studying medieval fortifications have repeatedly found evidence that builders possessed practical geometric knowledge far more sophisticated than previously assumed. Similar mysteries surround the construction of Carcassonne, the walls of Theodosian walls, and the mountain fortresses of the Crusader states. Sudak belongs to this same category of engineering puzzles. Water determines whether a fortress survives a siege. Food can be rationed, weapons can be repaired. But without water, even the strongest fortress eventually falls. Sudak sits on a rocky hill with limited natural freshwater resources. Historical records and archaeological investigations indicate the existence of large storage cisterns designed to collect and preserve water supplies. The engineering challenge was enormous. The Black Sea region experiences seasonal fluctuations in rainfall. During prolonged sieges, thousands of soldiers, civilians, and animals could require water every day. A single person typically requires at least 2 to 3 liters of drinking water daily under normal conditions. During military operations, requirements increase significantly. This means a garrison of only 1,000 individuals could consume several thousand liters every day. Researchers still debate the full capacity of Sudak's water storage network. Some believe extensive rainwater harvesting systems supplemented local springs. Others argue that additional supply routes may have existed outside the visible archaeological record. Whatever the answer, the fortress could not have functioned without sophisticated hydraulic planning. Perhaps the most fascinating engineering mystery of Sudak Fortress lies within the walls themselves. Many sections of the fortress were constructed during the Genoese period in the 14th and 15th centuries. More than 600 years later, substantial portions remained standing despite earthquakes, warfare, coastal weathering, temperature fluctuations, and centuries of neglect. From a materials science perspective, this is extraordinary. Modern concrete structures often require major maintenance after only a few decades. Steel reinforcement can corrode. Freeze-thaw cycles can crack masonry. Salt carried by sea winds can gradually destroy building materials. Yet Sudak continues to endure. The fortress was primarily constructed using local limestone and sandstone, bonded with lime mortar. At first glance, this appears simple. However, scientific studies of historical mortars across the Mediterranean have revealed surprising complexity. Many medieval builders mixed crushed ceramics, brick fragments, volcanic materials, and other additives into lime mortar. These ingredients could trigger chemical reactions similar to those found in Roman hydraulic concrete. Microscopic analysis of ancient mortars from Roman harbours has shown that certain mineral crystals continue strengthening structures centuries after construction. Researchers have discovered rare calcium aluminum silicate compounds that contribute to remarkable durability. Could similar processes have occurred within the walls of Sudak? Some material analyses suggest that medieval builders understood far more about mortar performance than written records indicate. The exact recipes, however, were rarely documented. Construction knowledge was often transmitted through apprenticeship rather than books. When master builders died, portions of their expertise disappeared with them. This pattern appears repeatedly throughout history. Roman concrete remains durable after nearly 2,000 years. The mortar used in parts of the Great Wall of China incorporated sticky rice compounds that improved strength. Medieval cathedral builders created structures that have survived for centuries despite constant environmental stress. Sudak Fortress may represent another example of lost materials technology. Scientists can analyze surviving samples, identify mineral compositions, and model chemical reactions. Yet, reconstructing the complete manufacturing process remains difficult because the human knowledge behind the materials has vanished. The walls still stand, the builders' methods remain partly hidden. Construction on Sudak's scale required an immense logistical operation. The fortress covers roughly 30 hectares and includes massive walls, towers, gates, defensive platforms, and internal structures. Every stone had to be quarried. Every stone had to be transported uphill. Every stone had to be positioned precisely. Today, cranes can lift dozens of tons with ease. Medieval builders relied on human labor, animal power, wooden scaffolding, pulleys, and lifting devices derived from ancient engineering traditions. Archaeologists estimate that large fortification projects often required hundreds or even thousands of workers operating over decades. Yet many questions remain unanswered. How was labor organized? How were materials supplied consistently? How were construction schedules coordinated? The fortress preserves the result, but not the process. Nestled in the mountains of southern Uzbekistan near the border with Tajikistan, Uzundara Fortress stands as one of the most remarkable surviving military strongholds of the Greco-Bactrian kingdom. Archaeological excavations that began in the early 2010 era revealed a remarkably well-preserved site dating to approximately the 3rd–2nd centuries BCE. Positioned high above a narrow mountain corridor, the fortress controlled one of the most strategic routes into ancient Bactria. Yet more than 2,000 years later, many of the engineering secrets behind its construction and operation remain unexplained. The first mystery begins with geography. Modern satellite analysis shows that Uzundara occupies an exceptionally advantageous location. The fortress overlooks a narrow mountain pass that naturally funnels movement through the region. Any army attempting to enter Bactria from the north would have been forced through this corridor, placing it directly under observation. What puzzles researchers is how ancient engineers identified such an ideal position without modern surveying equipment. Today, military planners use topographic mapping, aerial reconnaissance, satellite imagery, and computer simulations to evaluate defensive positions. Yet the builders of Uzundara possessed none of these technologies. Even so, they selected a location that military historians describe as remarkably efficient. The fortress commands extensive views across surrounding valleys while minimizing vulnerable approaches. Similar strategic positioning can be observed at Hellenistic fortifications in Afghanistan and parts of the former Seleucid Empire, but Uzundara stands out because of the complexity of its mountainous terrain. Some archaeologists believe generations of accumulated geographic knowledge may explain the choice, while others argue that Greek military surveyors developed practical methods capable of analyzing landscapes with surprising precision. Whatever the explanation, the decision demonstrates an understanding of terrain that rivals many later military systems. One of the most surprising discoveries concerns the scale of the defences. Excavations have revealed massive walls reinforced with numerous towers, carefully planned firing positions, and defensive arrangements capable of covering multiple attack routes simultaneously. Archaeologists have recovered thousands of arrowheads from the site, suggesting the fortress was heavily militarized. The mystery is that the defensive capacity appears unusually large for a remote frontier outpost. Military calculations indicate that a relatively modest garrison could effectively control the mountain pass, yet the fortress was built as though its designers expected sustained assaults by significant enemy forces. This naturally raises the question: who were these enemies? The Greco-Bactrian kingdom faced pressure from nomadic groups across Central Asia, including tribes originating from the Eurasian steppe. Historical records describe migrations and invasions occurring throughout the region during the centuries following Alexander the Great's campaigns. Some scholars suggest Uzundara may have formed part of a larger defensive system, protecting Bactria from these threats, while others believe the fortress defended economically important trade routes that connected Central Asia with emerging Silk Road networks. The true scale of the danger that inspired such extensive defences remains unknown. Perhaps the most fascinating engineering mystery concerns logistics. Military historians often emphasize that armies march on food, water, and supplies rather than weapons alone. Building a fortress is difficult, but keeping it operational for years is far more challenging. Uzundara stands hundreds of meters above surrounding valleys in rugged terrain, meaning every stone block, every weapon, every storage jar, and every food supply had to reach the site somehow. Excavations uncovered evidence of long-term occupation, including storage facilities, military equipment, and domestic artifacts. These findings indicate that soldiers lived and worked here continuously rather than occupying the fortress only during emergencies. This raises difficult questions about how much food was required annually, where water was obtained during dry seasons, and how construction materials were transported uphill. Modern military studies show that maintaining a mountain outpost often requires several times more logistical effort than supporting forces on flat terrain, and similar challenges confronted Roman garrisons in alpine regions centuries later. Yet the Greco-Bactrian kingdom managed to maintain Uzundara long before the development of many sophisticated logistical systems associated with Rome. The exact supply network remains largely invisible in the archaeological record. Uzundara lies more than 3,000 kilometers from Greece. Despite this enormous distance, many architectural features display unmistakable influences from Hellenistic military engineering traditions. The fortress demonstrates sophisticated planning, with towers positioned to maximize visibility and defensive coverage, wall segments exploiting natural rock formations, and defensive zones overlapping in ways that increased battlefield effectiveness. This raises a significant question. How did advanced engineering knowledge travel so far from the Mediterranean world? The campaigns of Alexander the Great spread Greek culture across vast territories, but maintaining technical expertise over such distances presented enormous challenges. Engineers, architects, military officers, and craftsmen would have needed to transfer specialized knowledge across generations. Some historians compare this process to the spread of Roman engineering throughout Europe centuries later, while others argue that local Central Asian traditions merged with imported Greek techniques, producing hybrid forms of military architecture unique to the region. Exactly how this knowledge was transmitted remains uncertain. No fortress operates in isolation. Researchers increasingly suspect that Uzundara formed part of a larger chain of military observation posts scattered across the frontier. If correct, this network would have allowed warnings to travel rapidly across great distances. The concept is not unprecedented. The Romans later developed extensive signaling systems along their borders. Ancient China employed beacon towers capable of transmitting alerts across hundreds of kilometers, and similar systems existed in the Byzantine and Islamic worlds. However, evidence suggests Uzundara may represent an earlier example of such frontier communication. The fortress occupies a position with exceptional visibility, and several nearby elevated locations could potentially have functioned as relay stations. Yet major questions remain unanswered. What signals were used? Smoke, fire, or reflective surfaces? How quickly could information travel? Could an invasion be reported within hours rather than days? Until additional sites are excavated, the communication system remains largely hypothetical. The mountains surrounding Uzundara present environmental challenges beyond warfare. Strong winds, seasonal temperature fluctuations, erosion, and seismic activity all threaten long-term structures, yet significant portions of the fortress survived for more than 2 millennia. Archaeologists have noted that many sections of the fortress incorporate natural bedrock directly into defensive structures. Rather than forcing the landscape to conform to a predetermined design, the engineers adapted their construction to existing geological features. This strategy reduced the amount of material required while increasing structural stability. Modern engineers often employ similar principles when designing infrastructure in mountainous regions. By integrating natural formations into construction plans, they reduce stress on artificial structures and improve resistance to environmental forces. The extent to which ancient builders consciously understood these principles remains debated, but the results nevertheless demonstrate remarkable practical knowledge. The final mystery concerns the fortress's disappearance. Archaeological evidence suggests that Uzundara was eventually abandoned during a period of regional instability associated with nomadic incursions and the decline of Greco-Bactrian power. Yet the abandonment appears surprisingly rapid. Many frontier fortifications throughout history evolve gradually, changing functions as political conditions shift. But Uzundara seems to have experienced a more abrupt fate. After centuries of development, the knowledge required to design, supply and operate such a sophisticated mountain fortress largely vanished from the region. This pattern appears repeatedly throughout history. The engineers who built Roman aqueducts disappeared, the specialists responsible for constructing massive Egyptian monuments vanished, and the craftsmen who created the Antikythera mechanism left behind almost no written explanation of their techniques. Uzundara presents a similar puzzle. The walls survive, the towers survive, and the artifacts survive, but the people who understood how the entire system functioned have disappeared from history. Situated on the edge of the ancient Khorazm oasis near the Kizilkum Desert in the Autonomous Republic of Karakalpakstan of Western Uzbekistan, Yanbas Kala stands as one of the region's most remarkable archaeological sites. The fortress was first scientifically documented during the Khorazm Archaeological and Ethnographic Expedition, led by Soviet archaeologist Sergei Tolstov in the 1930s. Dating evidence places its construction between the 4th century BCE and the 1st century CE during the rise of the Khorazm civilization. What appeared at first to be another ruined desert fortress soon revealed one of the most unusual military engineering systems in the ancient world. One of the strangest features of Yanbas Kala becomes obvious the moment its walls are examined. Unlike most major fortifications of antiquity, the fortress lacks projecting defensive towers. This is highly unusual. Greek fortresses, Persian strongholds, and later Roman military installations almost always relied on towers to create overlapping fields of fire. Towers allowed defenders to attack enemies approaching the walls from multiple directions and eliminated blind spots. Yanbas Kala followed a different strategy. The fortress occupied roughly 200 by 170 meters and was surrounded by walls reaching approximately 10 meters in height. Instead of placing towers at intervals, the builders incorporated continuous rows of arrow slits along the defensive walls. Hundreds of archers could fire simultaneously from protected positions inside the structure. The result may have created a nearly uninterrupted defensive perimeter. Some researchers suggest that this design compensated for the absence of towers by transforming the entire wall into a massive firing platform. The mystery is why. Military engineers across Eurasia had already demonstrated the effectiveness of towers for centuries, yet the architects of Yanbas Kala deliberately abandoned this proven design. Was it an adaptation to local warfare, a response to attacks by nomadic horse archers, or evidence of an independent military tradition developed within Khorazm itself? No written record survives to explain the decision. The walls themselves reveal another remarkable engineering achievement. Excavations showed that Yanbas Kala did not rely on a single defensive barrier. Instead, the fortress employed a sophisticated double-wall system. Between the outer and inner walls existed a network of corridors and fighting platforms from which defenders could move, coordinate, and launch attacks. This arrangement resembles concepts later associated with medieval concentric castles. In a conventional fortress, breaching the outer wall often provided attackers access to the settlement. At Janbuskala, penetrating the first barrier merely exposed invaders to a second layer of defense. The tactical advantage was enormous. An attacking force trapped between two walls could be subjected to arrow fire from multiple elevations. Defenders retained mobility while attackers became compressed within a confined space. Military historians often associate defense in depth with much later fortification systems. Yet Janbuskala appears to have employed a comparable principle more than 2,000 years ago. How Khwarezm engineers developed such an advanced defensive concept remains unclear. Most ancient fortresses were vulnerable at their gates. Walls could be thick, but every entrance represented a weakness. Janbuskala's architects addressed this problem through an unusually complex gate design. Archaeological evidence suggests that attackers entering the fortress could not simply rush through an open entrance. Instead, they were forced into a narrow passage where movement became restricted and predictable. This transformed the gateway into what modern military analysts would describe as a killing zone. Archers positioned above could fire directly into the confined space. Attackers lost the ability to maneuver effectively, while defenders enjoyed maximum visibility and protection. Comparable concepts later appeared in medieval gatehouses throughout Europe and the Middle East, where invaders could be trapped beneath murder holes and defensive galleries. Yet Janbuskala predates many of these examples by centuries. How ancient builders determined the optimal dimensions of this defensive trap remains unknown. Without modern mathematics, computer simulations, or engineering software, they somehow created a gateway specifically designed to maximize defensive efficiency. Constructing a fortress of this scale required more than manpower. The walls of Janbuskala follow a remarkably regular geometric layout. Measurements indicate that the structure maintained consistent alignment over distances approaching 200 meters. Today, engineers achieve such precision using GPS systems, laser levels, and electronic instruments. Ancient builders possessed none of these tools. To construct Janbuskala, surveyors first had to determine orientation. They then had to establish straight reference lines, maintain geometric consistency, and ensure that multiple construction teams followed identical measurements across the site. Similar questions surround famous monuments such as the Great Pyramid of Giza, whose sides align with true north to within a fraction of a degree, and Roman military camps that display astonishing geometric regularity. The problem is not that ancient people achieved precision. The problem is that the exact methods used to achieve that precision are often poorly documented or entirely lost. Janbuskala represents another example of technical knowledge surviving in stone and earth, while the procedures themselves disappear from history. Perhaps the greatest engineering challenge was not defense, but construction itself. Janbuskala stands within one of Central Asia's most demanding environments. Summer temperatures in the Kizilkum region can exceed 45 degrees Celsius. Water is limited, vegetation is sparse, and transportation was difficult long before modern roads existed. Yet thousands of tons of mud brick were transported, shaped, dried, and assembled into massive fortifications. The walls alone required extraordinary quantities of raw material. A single mud brick typically weighs several kilograms. Building defensive walls hundreds of meters long and up to 10 meters high would have required hundreds of thousands, perhaps millions of individual bricks. This raises difficult logistical questions. Where did the builders obtain sufficient water? How was labor organized? How were food supplies maintained for workers? How long did construction take? Ancient Egyptian pyramids, Roman military camps, and Mesopotamian city walls all required sophisticated administrative systems. Janbus Kala suggests that Khorasan possessed similar organizational capabilities, yet far fewer historical records survive. The engineering remains visible. The management system behind it remains largely invisible. No fortress can survive without water. This reality becomes even more critical in an arid environment such as ancient Khorasan. The region's civilization depended upon one of the largest irrigation systems in Central Asia. Archaeologists have identified traces of canals stretching across vast areas of the oasis, transforming otherwise inhospitable land into productive agricultural territory. Janbus Kala almost certainly relied upon this hydraulic network. However, much of the system has disappeared beneath shifting sediments, agricultural activity, and centuries of environmental change. Scientists know that water reached the fortress. They do not fully understand how. Did underground channels contribute to supply? Were reservoirs maintained inside the walls? How was water distributed during sieges? These questions remain unresolved. The mystery recalls similar debates surrounding the hydraulic systems of Petra and Jordan, the qanats of ancient Persia, and the underground water networks of Central Asian settlements. In every case, the surviving structures suggest levels of engineering sophistication that exceed what many people expect from ancient desert societies. Evidence discovered at Janbus Kala indicates that the fortress did not simply fade away. Archaeologists recovered numerous arrowheads concentrated around defensive sectors of the site. Burn layers and destruction debris suggest that the settlement experienced a violent military confrontation. The fortress appears to have been attacked and eventually abandoned. What happened remains uncertain. One possibility is that attackers breached the walls using siege techniques. Another proposes that changing political conditions rendered the fortress strategically unnecessary. Environmental pressures may also have weakened the agricultural systems supporting the population. The evidence provides fragments of a story, but not the complete narrative. Who attacked Janbus Kala? How large was the defending force? Did the fortress fall in a single assault or after a prolonged siege? No surviving text answers these questions. Horvat Ethri is an archaeological site located in the Judean foothills of central Israel, approximately 35 kilometers southwest of Jerusalem. The site was extensively excavated between 1999 and 2001 by archaeologists Boaz Zissou and Amir Ganor of the Israel Antiquities Authority. What appeared at first to be the remains of an ordinary rural settlement soon revealed something far more remarkable beneath the surface. An elaborate network of underground tunnels, water systems, storage chambers, and hidden passages carved directly into bedrock. The village flourished during the late Second Temple period and remained occupied until the Bar Kokhba revolt against Rome between 132 and 136 CE. Today, nearly 2,000 years later, Horvat Ethri continues to raise questions about the engineering capabilities of its builders. The most extraordinary feature of Horvat Ethri lies below ground. Archaeologists discovered a vast system of interconnected underground chambers carved into the limestone bedrock. Narrow tunnels linked storage rooms, cisterns, hiding complexes, and concealed exits. Some passages are so tight that modern researchers must crawl through them. The purpose of these tunnels is generally associated with the Bar Kokhba revolt. Jewish rebels throughout Judea created underground refuge systems to evade Roman forces. However, Horvat Ethri presents a deeper mystery. The complexity of the network suggests long-term planning rather than emergency construction. Excavations indicate that many tunnels were connected to private homes, allowing residents to disappear underground within seconds. Some chambers were hidden behind movable stones or concealed entrances that would have been nearly impossible for outsiders to detect. What puzzles researchers is the engineering involved. The builders excavated large volumes of rock while preserving the structural stability of buildings above. Modern mining engineers understand that underground excavation creates stress fractures that can lead to collapse if support systems are inadequate. Yet many of Horvat Ethri's chambers remained intact for nearly 2 millennia. How did ancient builders determine where to cut, how much rock to remove, and which sections could safely support the weight above? No written construction manuals have survived. Even more intriguing is the apparent coordination required to connect separate chambers. Without laser surveying equipment, GPS technology, or modern mapping systems, builders achieved a level of underground integration that resembles military engineering projects from much later periods. Similar hiding systems have been discovered at Horvat Midras and other Judean sites, but Horvat Ethri remains among the most sophisticated examples ever found. The Judean foothills experience long dry seasons and highly variable rainfall. Water management was therefore essential for survival. At Horvat Ethri, archaeologists uncovered multiple cisterns, ritual baths known as mikvaot, storage reservoirs, and water collection systems integrated directly into the natural topography. The engineering challenge was considerable. Rainwater had to be collected during limited seasonal storms and preserved for months. A single family could require thousands of litres of water annually for drinking, cooking, agriculture, and ritual activities. Researchers estimate that some ancient cistern systems throughout Judea could store tens of thousands of litres of water. The cisterns at Horvat Ethri were carefully positioned to maximise runoff collection while minimising contamination and evaporation. The mystery lies in the planning. Modern hydrologists use computer models to predict water flow. Ancient builders relied entirely on observation and experience. Yet their systems often achieved remarkable efficiency. Comparisons with other ancient civilizations are revealing. The Nabateans of Petra developed sophisticated desert water systems. Roman engineers constructed aqueducts spanning hundreds of kilometers. Horvat Ethri was much smaller, but the villagers faced similar environmental challenges and solved them using entirely local resources. The knowledge required to design such systems was clearly practical and highly developed. Yet almost none of it was recorded. The technology survived. The instruction manuals vanished. Every underground chamber at Horvat Ethri required the removal of solid limestone. This may sound straightforward until the scale of the work is considered. Limestone has a compressive strength ranging from approximately 30 to over 250 megapascals depending on composition. Removing large volumes with iron chisels, hammers and hand tools demanded enormous labour and technical skill. Archaeologists have identified quarrying marks throughout the site, indicating systematic excavation techniques rather than random digging. The walls of many chambers display surprisingly regular surfaces. Passageways often follow efficient routes that minimize unnecessary excavation. Storage rooms exhibit dimensions carefully adapted to the surrounding geology. This raises an important question. How much geological knowledge did the builders possess? Modern engineers conduct rock stability analyses before excavation projects. Ancient workers lacked such methods, yet repeatedly created durable underground structures. Evidence suggests that generations of accumulated expertise may have guided construction. Builders likely learned to identify fracture patterns, evaluate rock quality, and recognize signs of instability. However, because these skills were transmitted orally, most of that technical knowledge disappeared forever. What survives are the results, not the methods. Horvat Ethri was not a major city. Its population was likely measured in hundreds rather than thousands. Yet archaeologists discovered substantial fortification features and defensive planning integrated into the settlement. The village occupied a strategically elevated position approximately 406 meters above sea level. Buildings, roads, storage facilities, and underground systems were arranged in ways that enhanced security. The hidden tunnel network itself functioned as a defensive technology. Roman military doctrine depended upon visibility, control of movement, and overwhelming force. Underground refuges disrupted all three advantages. Rebels could disappear, relocate, store supplies, and emerge unexpectedly. This strategy resembles forms of asymmetric warfare still studied by military historians today. What remains unclear is how early these preparations began. Were residents responding to growing tensions with Rome? Were they drawing upon older regional traditions of defensive architecture? Or did the village occupy a strategically important position that modern researchers have not yet fully understood? The answers remain elusive. Perhaps the most overlooked mystery involves measurement itself. Everything at Horvat Ethri required accurate spatial planning. Buildings had to align with terrain, cisterns had to occupy optimal locations, underground chambers had to avoid structural failure. Drainage systems had to maintain functional gradients. Today, surveyors use total stations, satellite positioning systems, laser scanners, and digital terrain models. Ancient builders possessed none of these technologies, yet they consistently produced workable solutions. Experimental archaeology has demonstrated that simple tools such as plumb lines, measuring rods, ropes, and water levels can achieve surprisingly high accuracy. Egyptian pyramid builders, Roman engineers, and Greek architects all relied upon such methods. Nevertheless, Horvat Ethri demonstrates that these skills were not limited to imperial capitals or monumental construction projects. Even a rural village possessed technical knowledge capable of transforming a rocky hillside into a highly organized settlement. The mystery is not whether the builders succeeded. The mystery is how much knowledge was required to make success possible. Large engineering projects require organization. Someone must design plans, workers must excavate tunnels, stone must be removed, water systems must be maintained, food must support laborers, construction schedules must be coordinated. The archaeological evidence suggests that Horvat Ethri functioned through a surprisingly sophisticated level of community cooperation. The underground network was not the work of a single family. Its scale implies participation by many individuals over extended periods. Comparisons with modern construction projects highlight the challenge. Even relatively small underground infrastructure projects require planning, labor, allocation, logistics, and quality control. Yet the people responsible for Horvat Ethri left no names, no records, and no technical documents. Their accomplishments survive. Their identities do not. St. Simeon Monastery stands on the west bank of the Nile near Aswan in southern Egypt. The massive complex was first documented by European travelers during the 19th century and later examined by archaeologists studying the development of early Christian communities in Egypt. Built between the 7th and 10th centuries CE and abandoned around the 13th century, the monastery remains one of the largest surviving desert monastic settlements ever discovered in North Africa. At first glance, it appears to be little more than a ruined religious complex. Yet closer examination reveals something far more intriguing: a self-sustaining fortress city constructed in one of the harshest environments on Earth. The mystery is not why monks lived here. The mystery is how they managed to survive here at all. The greatest mystery of St. Simeon begins with a simple question: where did the water come from? The monastery sits on elevated ground overlooking the Nile. This location provided strategic advantages, including visibility and protection from flooding, but it created a severe logistical problem. Every litre of water needed for drinking, cooking, washing, agriculture, and animals had to be transported uphill. Archaeological surveys have revealed large cisterns, storage basins, channels, and collection systems integrated throughout the complex. These installations indicate sophisticated water management rather than simple manual transport. Scientists estimate that an average person living in an arid environment requires at least several litres of water daily for survival. If St. Simeon housed between 300 and 1,000 residents, annual consumption could have reached millions of litres. The challenge becomes even more remarkable when considering Aswan's climate. Modern rainfall averages only a few millimetres per year, meaning water harvesting alone could not have sustained such a population. Some researchers suggest that caravans and animal transport systems carried water from the Nile, while others argue that a highly organised supply infrastructure connected the monastery to river-based distribution networks. Yet no complete blueprint of the system survives, and the exact mechanism that sustained hundreds of people for centuries remains one of the monastery's greatest unsolved engineering puzzles. Religious communities generally build places of worship, but St. Simeon built defensive walls. The monastery is surrounded by massive fortifications reaching approximately 10 meters in height, and the outer walls resemble military architecture more than traditional religious construction. Why would monks require defenses on such a scale? The answer may lie in the monastery's location along important trade routes linking Egypt with Nubia and regions farther south. Historical records indicate periods of political instability, tribal conflict, and raids across the region. Yet the engineering itself remains remarkable. The builders used mud bricks reinforced through techniques that allowed the walls to withstand centuries of erosion, temperature fluctuations, and desert winds. Even after hundreds of years of abandonment, significant sections remain standing. Modern engineers understand how difficult it is to preserve earthen architecture, and many contemporary mud brick structures deteriorate rapidly without maintenance. St. Simeon's walls survived nearly a millennium, yet the exact construction methods, material mixtures, and maintenance procedures employed by the builders remain only partially understood. Most large settlements are built on relatively flat terrain, but St. Simeon was not. The monastery occupies a steep desert hillside where elevation changes create major architectural challenges. Instead of leveling the landscape, the builders designed a complex system of terraces, stairways, courtyards, storage chambers, workshops, and residential quarters integrated directly into the terrain. This required advanced planning. Every wall had to account for slope stability, every foundation had to support structures above and below it, and every pathway had to connect different sections efficiently while allowing movement of people, animals, food, and construction materials. Modern archaeological mapping reveals a carefully organized layout rather than random expansion. The design resembles some Byzantine fortified settlements and certain mountain monasteries found throughout the eastern Mediterranean. However, no written construction manuals from St. Simeon have survived. As a result, researchers can observe the engineering solution but cannot fully reconstruct the design process behind it. Water was not the only challenge. Food represented an equally complex problem. Excavations have uncovered granaries, storage facilities, kitchens, animal enclosures, and work areas distributed throughout the monastery. These discoveries indicate that St. Simeon functioned as a large economic centre rather than a simple place of worship. To sustain hundreds of residents, enormous quantities of grain, vegetables, oil, and livestock products would have been required. Archaeologists estimate that a community of several hundred people could consume dozens of tons of food annually. The surrounding desert provided little agricultural potential, so supplies had to arrive continuously from the Nile Valley or associated trade networks. This raises another question. How did the monastery coordinate transportation, storage, preservation, and distribution of resources across centuries? The organisational complexity begins to resemble that of a small medieval city, yet much of the administrative system responsible for this achievement has disappeared from history. One of the most overlooked mysteries involves the monastery's construction materials. Many visitors assume the walls are simple mud bricks, but scientific studies suggest otherwise. Ancient builders often modified mud brick mixtures using combinations of clay, sand, straw, organic fibres, and mineral additives. These ingredients could dramatically affect durability, insulation, and resistance to cracking. St. Simeon exists within an environment where daytime temperatures can exceed 40 degrees Celsius, while nighttime temperatures drop significantly. Such thermal stress normally causes rapid deterioration, yet portions of the monastery have survived for nearly 1,000 years. Researchers continue to analyze surviving brick samples to understand how their composition contributed to long-term stability. Some results suggest an impressive understanding of local materials and environmental adaptation. The builders may not have possessed modern chemistry, but they clearly understood practical material science. Exactly how much knowledge they possessed remains uncertain. For centuries, historians imagined desert monasteries as isolated communities, but St. Simeon tells a different story. Excavations have uncovered imported ceramics, foreign goods, and evidence of commercial interaction extending beyond the immediate region. Its position near major Nile and caravan routes likely transformed the monastery into an important waypoint, connecting Egypt with Nubia and sub-Saharan trade networks. Ideas travelled alongside merchants, and technologies travelled alongside ideas. Construction techniques, agricultural practices, storage methods, and engineering knowledge could have moved across enormous distances through these networks. The monastery may have functioned not only as a religious centre, but also as a hub for technological exchange. Yet the exact routes through which knowledge reached St. Simeon remain poorly understood. The archaeological evidence reveals the connections, but the historical details remain frustratingly incomplete. Toro Muerto is one of the largest and most mysterious rock art complexes ever discovered. Scattered across the Madres Valley in southern Peru, approximately 150 kilometers northwest of Arequipa, thousands of volcanic boulders are covered with carvings that have survived for centuries beneath the desert sun. Archaeologists estimate that more than 5,000 engraved stones occupy an area of roughly 10 square kilometers, making Toro Muerto larger than many famous petroglyph sites found elsewhere in the Americas. Yet despite decades of study, researchers still cannot fully explain who created this immense stone archive, how such a vast project was organized, or what messages its creators intended to preserve. The site was first systematically documented during the mid-20th century, particularly through the work of Peruvian researchers, including Eloy Linares Malaga. Archaeological evidence suggests that most carvings were produced between approximately 500 and 1500 CE, during periods influenced by cultures such as Wari, Chuquibamba, and later regional societies. However, establishing exact dates remains difficult because rock carvings contain little organic material suitable for radiocarbon dating. This uncertainty represents the first layer of the mystery. Scientists can estimate when the carvings were created, but the precise timeline remains elusive. The first great mystery concerns scale. Toro Muerto contains thousands of individual petroglyphs. By comparison, many famous rock art sites around the world contain only hundreds of carved panels. The concentration of engraved stones at Toro Muerto is extraordinary. Walking through the site feels less like exploring an archaeological monument and more like entering an enormous open-air archive. researchers have documented human figures, animals, geometric designs, abstract symbols, and complex compositions distributed across countless boulders. The sheer volume raises an important question. Why would ancient societies invest such enormous amounts of labour into carving stones spread across a desert landscape? Creating a single petroglyph is not a simple task. Ancient artists first had to remove the dark weathered surface known as desert varnish from volcanic rocks. This process required repeated hammering, pecking, grinding, and polishing. Experimental archaeology has shown that even relatively simple designs can require several hours of work. More detailed carvings may require days. When multiplied across thousands of stones, the labour investment becomes staggering. Some estimates suggest that the cumulative effort may have required tens of thousands of working hours. Such a project implies long-term planning, skilled artisans, and organised social cooperation. Yet no evidence of a centralised authority responsible for directing this effort has been found. The second mystery involves the remarkable durability of the carvings. Many petroglyphs remain clearly visible despite centuries of exposure to one of the harshest environments on Earth. Southern Peru experiences intense solar radiation, dramatic temperature fluctuations, seasonal flooding, and wind-driven erosion. Under such conditions, exposed surfaces normally deteriorate gradually. Yet many Toro Muerto carvings remain surprisingly well preserved. Scientists believe part of the explanation lies in the volcanic nature of the stone itself. The dark outer layer formed through long-term chemical weathering creates a natural protective surface. Ancient artists carefully removed this layer only where they wanted images to appear. The resulting contrast between the lighter carved areas and darker surrounding surfaces allowed designs to remain visible for centuries. However, researchers still debate whether the artists intentionally selected specific rock types because of their long-term preservation characteristics. If they did, this would indicate a practical understanding of geological properties that was far more sophisticated than often assumed. The third mystery centers on the famous dancers of Toro Muerto. Among the most recognizable figures at the site are strange human-like forms with raised arms, bent legs, elaborate head decorations, and exaggerated body proportions. Archaeologists often refer to them as dancers because their poses resemble movement or ritual performance. Yet nobody knows what these figures truly represent. Some researchers believe they depict ceremonial dances associated with religious rituals. Others suggest they may represent shamans experiencing altered states of consciousness. A few scholars have proposed that the figures symbolize supernatural beings rather than ordinary humans. What makes the mystery especially intriguing is that many of these images differ significantly from artistic traditions found elsewhere in the Andes. The figures appear almost unique to Toro Muerto, suggesting the existence of symbolic systems that have completely disappeared from history. The fourth mystery involves communication. Hundreds of carvings contain recurring geometric patterns that appear repeatedly across the site. Spirals, grids, circles, zigzags, intersecting lines, and abstract arrangements occur with remarkable frequency. The repetition suggests that these were not random decorations. Instead, they may have conveyed specific meanings understood by ancient viewers. Some archaeologists have explored the possibility that Toro Muerto functioned as a form of pre-literate information storage. While there is no evidence that the carvings constitute a true writing system comparable to Egyptian hieroglyphs or Mesopotamian cuneiform, the consistent use of repeated symbols suggests organized communication. If this interpretation is correct, Toro Muerto may represent one of the largest surviving repositories of symbolic information in pre-Columbian South America. Unfortunately, without a bilingual inscription equivalent to the Rosetta Stone, decoding the system remains nearly impossible. The fifth mystery concerns astronomy and landscape alignment. Certain researchers have noticed that some carved stones appear positioned in ways that relate to surrounding mountains, valleys, and celestial events. The Andes have a long history of integrating astronomy into ritual life. Civilizations such as the Inca developed sophisticated methods for tracking solstices, equinoxes, and seasonal cycles. Because agricultural success often depended upon accurate timing, celestial observations played a critical role in survival. At Toro Muerto, however, evidence remains inconclusive. Some alignments may be intentional, while others could simply be coincidental. The challenge lies in distinguishing genuine astronomical planning from patterns created by chance among thousands of stones. Even so, the possibility that portions of the site served as a landscape-scale ceremonial observatory continues to attract scholarly interest. The sixth mystery involves trade and cultural interaction. The Maids Valley occupied an important position connecting coastal Peru with the high Andes. Archaeological evidence suggests that people, goods, technologies, and ideas moved through this region for centuries. This raises an intriguing possibility. Toro Muerto may not have been created by a single culture at all. Instead, the site may represent a cumulative record produced by multiple societies over hundreds of years. Different groups could have added carvings generation after generation, transforming the landscape into a shared ceremonial and cultural center. Similar processes occurred at other major sacred sites around the world. Göbekli Tepe evolved through successive construction phases. Stonehenge developed over more than a millennium. Even the Nazca lines underwent modifications across multiple generations. If Toro Muerto followed a similar pattern, it may represent a collaborative cultural project extending far beyond the lifespan of any single community. The seventh mystery concerns the absence of accompanying settlements. Archaeologists have identified evidence of occupation in the wider region, but Toro Muerto itself lacks the large urban infrastructure one might expect for a project of such scale. There are no massive temples, palaces, or fortified cities directly associated with the carvings. This discrepancy creates a fascinating puzzle. How did ancient populations organize, coordinate, and maintain activity at such a vast site without constructing monumental architecture nearby? One possibility is that Toro Muerto functioned primarily as a pilgrimage destination. People may have traveled there seasonally for ceremonies, festivals, trade gatherings, or ritual activities. Similar patterns can be observed at sacred landscapes worldwide, where symbolic importance outweighed permanent habitation. Yet direct evidence remains limited. Located in the rugged highlands of the South Caucasus, a region that has served as a crossroads between Europe and Asia for thousands of years, Horvat Kur stands as one of the area's most intriguing archaeological sites. Archaeologists identified the settlement through surveys of elevated defensive positions scattered across mountain ridges and strategic valleys. Although partially ruined, surviving stone walls, defensive structures, and habitation remains reveal that Horvat Kur once occupied a commanding position over important travel and trade routes. What makes the site remarkable is not its size, but the engineering knowledge hidden within its stones. The ruins raise questions about construction techniques, resource management, military planning, and environmental adaptation that remain only partially understood today. The first mystery concerns the construction of Horvat Kur itself. The fortress occupies naturally defensive terrain characterized by steep slopes, rocky outcrops, and difficult access routes. Modern visitors often struggle to reach similar mountain fortifications even with contemporary equipment. Yet ancient builders successfully transported thousands of kilograms of stone uphill and assembled durable defensive walls without cranes, trucks, steel tools, or mechanized lifting systems. Archaeological evidence indicates that many sections of the fortification were built directly into the natural bedrock. Builders carefully adapted wall alignments to existing geological features, reducing structural stress while maximizing defensive strength. This approach resembles techniques observed at sites such as Machu Picchu in Peru and several Eurasian fortresses throughout Armenia and eastern Turkey. Researchers estimate that even a modest defensive wall measuring 100 meters in length, 3 meters in height, and 2 meters in thickness would require hundreds of cubic meters of stone. Depending on rock density, such a structure could contain well over 1,000 metric tons of material. The mystery is not simply how the stones were moved. The greater question is how ancient engineers planned and coordinated such a project in a mountainous environment where transportation itself was one of the greatest obstacles. No written construction manuals survive. No detailed engineering plans have been discovered, yet the walls still stand. One of the most impressive features of Horvat Kör is its longevity. Earthquakes are common throughout the Caucasus region. Over thousands of years, seismic activity, temperature fluctuations, rainfall, erosion, and vegetation growth should have severely damaged any poorly designed structure. Yet portions of the fortification remain recognizable today. This suggests that the builders possessed practical knowledge of structural stability that extended far beyond simple stone stacking. Ancient masons appear to have understood how to distribute weight, anchor walls to bedrock, and use the terrain itself as a stabilizing force. Modern structural engineers use mathematical models, computer simulations, and geotechnical surveys to evaluate slope stability. The builders of Horvat Kör had none of these tools. Instead, they relied upon accumulated experience passed from one generation to another. The exact methods used to determine safe wall placement remain unknown. This mystery resembles similar questions surrounding Iron Age hill forts in Britain, Celtic oppida in continental Europe, and mountain fortresses throughout the Caucasus. The monuments survive, but the engineering knowledge behind them has largely disappeared. Before construction could begin, someone had to survey the landscape. This may be one of the least appreciated technological achievements associated with Horvat Kör. The fortress occupies a position that offers extensive visibility across surrounding valleys. Defensive towers and wall sections appear deliberately arranged to maximize observation while minimizing vulnerable blind spots. Modern military planners rely on topographic maps, aerial photography, satellite imagery, and computer-generated visibility analyses. Ancient builders relied solely on direct observation, yet they achieved remarkably effective defensive positioning. Researchers studying ancient fortifications frequently observe that successful strongholds often occupy locations capable of monitoring major routes while remaining difficult to attack. Horvat Kör appears to follow exactly this principle. The mystery lies in how accurately ancient surveyors could evaluate terrain using only simple tools. Were they using ropes, measuring rods, sighting devices, or techniques that left no archaeological traces? The evidence remains incomplete. A fortress cannot survive without water. This simple fact creates one of Horvat Kör's greatest mysteries. Mountain fortifications face a unique challenge. Elevated locations provide excellent defense but often lack reliable access to rivers and springs. During a siege, defenders could be cut off from external water sources for weeks or even months. Archaeologists have identified evidence suggesting systems for collecting and storing water within similar Caucasian fortresses. Rock-cut reservoirs, cisterns, channels, and rainwater collection features appear at numerous sites throughout the region. If Horvat employed comparable systems, its builders would have needed sophisticated understanding of hydrology and resource management. Consider the mathematics. A population of only 200 individuals requires hundreds of litres of water every day for drinking, food preparation, and basic survival. Over a month-long siege, water demand could exceed 100,000 litres. Providing such quantities requires careful planning. Storage capacity must be calculated, rainfall patterns must be understood, and evaporation losses must be minimised. Yet no written records explain how these calculations were performed. The engineering knowledge exists only in the surviving architecture. Horvat may never have functioned as an isolated fortress. Instead, it may have been part of a larger defensive system stretching across mountain corridors. Many ancient fortifications throughout the Caucasus occupy positions with direct lines of sight to neighbouring strongholds. Such arrangements create the possibility of long-distance communication networks. Fire signals represent one possible explanation, smoke signals provide another, and reflective signalling using polished surfaces has also been proposed at various ancient sites around the world. Experimental studies demonstrate that signal fires can transmit warnings across dozens of kilometers within minutes if stations are properly positioned. Similar systems were documented in ancient China, Rome, Byzantium, and medieval Europe. If Horvat participated in such a network, its strategic value would have extended far beyond its physical walls. The mystery is that direct evidence remains scarce. The towers survive, but the communication methods do not. Building Horvat required more than engineering knowledge. It required social organization. Every stone had to be quarried, every block had to be transported, and every wall had to be assembled. Workers required food, tools, shelter, and coordination. Modern construction projects generate extensive paperwork documenting labour, logistics, and supply chains. Ancient projects rarely leave such records. As a result, archaeologists can estimate labour requirements, but often cannot identify the individuals responsible. This creates a fascinating paradox. The fortress clearly demonstrates organised collective effort, yet the people who coordinated that effort remain almost completely anonymous. Who directed construction? How was labour assigned? How were resources distributed? The answers remain unknown. Mary Gyal-Kala, located in present-day Turkmenistan near the ancient Murgab River oasis, was once one of the largest cities on the Silk Road. Behind its massive mud brick walls lies a technological mystery that archaeologists are still trying to understand. How did ancient engineers build, supply, defend and industrialize a city in the middle of one of Central Asia's harshest environments nearly 2,000 years ago? The ruins of Gyal-Kala were known to local populations for centuries, but systematic archaeological investigations began in the late 19th century and expanded significantly during Soviet expeditions throughout the 20th century. Modern excavations conducted by the International MERV project have revealed a vast urban landscape covering approximately 360 hectares, exposing evidence of sophisticated engineering, industrial production, and urban planning that exceeded previous expectations. At first glance, Gyal-Kala appears impossible. The city was built primarily from mud brick, a material that modern engineers consider vulnerable to erosion, rain, temperature fluctuations, and wind damage. Yet large sections of its walls remain visible after nearly 2,000 years. The fortifications enclosed an area of approximately 4 square kilometers, and some surviving wall sections still rise more than 10 meters above the surrounding terrain. Archaeologists estimate that millions of mud bricks were required to construct the defensive system alone. The question is simple. How did builders working without modern chemistry create earthen structures capable of surviving centuries of warfare, earthquakes, floods, and desert weather. Studies indicate that the bricks were manufactured from carefully selected clay-rich sediments combined with organic materials. However, researchers still debate the precise composition of the mixtures and the engineering principles behind their remarkable durability. Similar questions surround other ancient earthen structures such as the walls of Babylon and portions of the Great Wall of China. Yet Archaeological presents an even greater challenge because it survived within an environment characterized by extreme temperature variation and powerful seasonal winds. The builders clearly understood properties of soil stabilization long before modern geotechnical engineering emerged, although exactly how much they understood remains uncertain. Viewed from above, Archaeological reveals another puzzle. The city was constructed with a remarkably regular plan, and massive defensive walls form a near-rectangular enclosure stretching approximately 2 kilometers from side to side. Creating such a design required more than construction skill, it required surveying. Today, engineers rely on laser instruments, satellite positioning systems, digital terrain models, and advanced measurement equipment. Yet ancient surveyors possessed none of these technologies. Even so, they successfully laid out enormous walls, aligned gates, organized streets, and coordinated large-scale construction projects across hundreds of hectares. The challenge becomes even more impressive when considering the city's multiple construction phases. Archaeological evidence indicates that successive generations repeatedly reinforced, expanded, and modified the fortifications while maintaining overall structural coherence. This level of long-term planning suggests the existence of technical traditions passed from one generation to another. The buildings survived, but the manuals that explained how to build them did not. No city can exist without water, and this creates one of Archaeological's greatest mysteries. The city stood within the Murghab Oasis, surrounded by landscapes that today appear semi-arid and unforgiving. Summer temperatures regularly exceed 40 degrees Celsius, rainfall is limited, and agriculture without irrigation would have been impossible. Yet historical records indicate that Merv supported populations numbering in the tens or perhaps hundreds of thousands during various periods of its history. Such numbers required extraordinary quantities of water. Researchers have identified traces of ancient canals connected to the Murghab river system. These channels transported water across vast distances, supporting agriculture, industry, and urban life. However, much of the original network has disappeared. Sand accumulation, river migration, erosion, and centuries of human activity have erased significant portions of the hydraulic system. The remaining evidence raises difficult questions. How were gradients calculated? How was water flow regulated? And how are canals maintained across enormous distances? Hydraulic engineers understand that even small errors in slope can cause catastrophic failures in irrigation systems. Excessive slope accelerates erosion, while insufficient slope prevents water movement. Ancient engineers somehow achieved a balance precise enough to sustain one of Central Asia's most important urban centers, yet their calculations remain largely invisible. Among all the technological enigmas of Archaeological, none may be more surprising than its industrial zones. Excavations conducted by the International MERV project uncovered evidence suggesting large-scale metallurgical activity inside the city. What archaeologists found was not merely a collection of small workshops, they discovered an organized industrial landscape. Several furnace complexes, slag deposits, ash layers, production debris, and specialized working areas indicate that metal production occurred on a scale far greater than previously assumed. This discovery transformed how researchers viewed the city. For decades, Gyar-Kala was primarily regarded as a commercial and administrative centre along the Silk Road, but the industrial evidence revealed something else. It was also a manufacturing centre. The furnace remains suggest that ancient metallurgists possessed sophisticated knowledge of airflow control, combustion management, and high-temperature production processes. Producing iron and steel is far more complicated than simply heating metal. Ancient craftsmen had to maintain temperatures approaching or exceeding 1,100 to 1,300 degrees Celsius, depending on the process. Achieving such conditions consistently required careful fuel selection, furnace design, and oxygen management. Without thermometers, pressure gauges, or laboratory equipment, metalworkers relied entirely on experience and observation. Yet the archaeological evidence suggests remarkable consistency. Some furnace structures appear to have incorporated controlled air intake systems that improved combustion efficiency. Researchers have identified evidence of tuyères, ceramic air nozzles used to direct oxygen into furnaces. This technology dramatically increases achievable temperatures, and the same principle remains fundamental in modern blast furnace operations. The mystery deepens when examining production scale. Certain industrial zones contain substantial accumulations of slag, the waste material generated during metal extraction and refining. Large slag deposits typically indicate repeated production cycles over long periods, suggesting organized manufacturing rather than occasional local metalworking. But where did the technical knowledge originate? Some scholars propose influences from Persian metallurgical traditions, while others point to connections with technologies moving along Silk Road trade routes from India, China, or the Near East. No consensus exists. Even more puzzling is the possibility of still production. Several researchers have suggested that certain furnace remains may have been capable of supporting advanced iron working processes. If true, Gyar-Kala's craftsmen would have belonged to a technological tradition comparable to some of the most sophisticated metallurgical centres of the ancient world. For comparison, Roman iron production centres in Europe, Parthian workshops in Iran, and Indian steel-making traditions all required highly specialized expertise. The craftsmen of Gyar-Kala appear to have possessed similar capabilities, yet almost nothing is known about the individuals themselves. Their names are lost, their methods are lost, and only the industrial scars they left in the ground remain. Gyar-Kala was more than a fortress or industrial centre. It was a crossroads of civilizations. Archaeologists have found evidence of Zoroastrian, Buddhist, Christian, and Islamic communities, reflecting centuries of cultural diversity. This mix of cultures may explain the site's technological sophistication, as ideas and innovations travelled along the Silk Road through trade and migration. Gyar-Kala may have served as an ancient hub for knowledge exchange, though exactly how this technology spread remains unclear.